the seabed dynamics that expose them are not going to stop. If anything, increased storminess, ongoing trolling, and the constant churn of construction will keep stirring the North Sea floor for centuries. That means more bones, more tools, more fragments will almost certainly surface. The question is whether we can move from treating them as rare accidents to treating them as clues. Clues that can guide us toward the first truly mapped and excavated human landscapes under the North Sea. And perhaps toward the moment when we stop asking whether Doggerland people are out there and start listening to what their remains are actually trying to tell us. If stray bones and tools are just the flares, the obvious next question is what happens if we actually follow them back to their source. Up to now, most of Doggerland has been a kind of statistical landscape. We know where rivers once flowed, where marshes formed, where coastlines crept and retreated. We can model floodplains, lakes, estuaries, but we almost never get to see a specific place frozen in time the way we do at famous dryland sites. That might be about to change. The same engineering work that churns up the seabed is also pushing our maps from broad brush sketch to street-level detail. When offshore wind developers or cable planners survey a patch of the North Sea today, they survey a patch of the North Sea today. They're not just firing a few low-resolution sonar lines and calling it done. They're running densely spaced grids of multi-beam echo sounders, high-frequency seismic profilers, and subbottom images that can pick out buried channels a few meters wide and peak lenses less than a meter thick. Put enough of that data together, and Doggerland stops being an abstract name. It becomes a place with neighborhoods. You can already see this shift in a few well-studied areas. Shallow banks that used to be mapped as anonymous sand bodies now resolve into former hilltops. Linear features once dismissed as geological noise turn out to be ancient river levees and oxbow lakes. Narrow ridges align into something suspiciously like old trackways, natural high ground where people would have walked, hunted, and camped above the surrounding marsh. Those are exactly the kinds of places where intact settlement areas are most likely to survive. On land, Mesolithic people in northwest Europe loved certain kinds of spots. Slightly raised unless beside fresh water, the edges of wetlands where you could reach both open water and dry ground. Narrow land bridges between larger masses of land. If you dropped a pin on a Mesolithic map at Small Bluff over a channel junction, you'd have a decent chance of landing on a campsite under the North Sea. Those bluffs and junctions are still there, buried, softened, but not erased. When we trace an old river and see a little bump on its inside bend, or a pinch point where two valleys squeeze together before opening out onto a floodplain, we're essentially looking at a short list of Vivas P addresses, strong candidates for human occupation. Now add another layer, environmental DNA. In the last few years, researchers have started pulling something astonishing out of seabed cores. Traces of genetic material from organisms that lived there thousands of years ago. Not intact DNA strands from a specific mammoth or human, but a kind of biological dust. Little fragments shed in skin cells, hair, feces, plant tissue that get locked into sediments. Processed the right way, that dust becomes a community snapshot. Take a core from a buried Doggerland lake bed. Run environmental DNA analysis. You might get a list that reads birch, willow, hazel, grasses, sedges, carp, pike, elk, red deer, beaver, wild pig. From that list alone, you can reconstruct a living environment with more precision than you'll ever get from pollen counts or a handful of beetle shells. You can see whether the forest was dense or patchy, whether the shoreline was marshy or firm, whether there were fish big enough to justify permanent settlements. More importantly, you can start to pick out human fingerprints without actually finding a bone. Environmental DNA can flag the presence of domestic dog or of plants that tend to thrive around human disturbance. It might even in some cases preserve enough human DNA to say humans were here long before a troll net brings up a skull fragment. That means we don't have to wait passively for hunters and wind farm foundations to get lucky. We can go looking proactively using Edna as a kind of scent trail. Combine that with more precise dating and things get really interesting. Right now, many Dogon finds land in pretty broad time brackets: early Mesolithic, late Mesolithic, sometimes Neolithic. Radiocarbon dating on a single bone or piece of wood gives us a window of a few hundred years, maybe a bit better with improved calibration curves. Ancient DNA analysis on bones can tie individuals into family trees and broader population histories, but techniques are sharpening. Compound-specific radiocarbon dating can target particular amino acids in bone collagen. Bayesian modeling can weave dozens of individual dates into tighter timelines, especially when linked to well-understood climate events or sea level markers. Thermoluminescence and optically stimulated luminescence can date the last time sand grains were exposed to light, which is crucial for understanding when exactly a surface was last walked on before drowning. Put that package together: high-resolution maps, environmental DNA to tell you where life clustered, improved dating to pin down when. And you suddenly have the tools to hunt not just for Doggerland in general, but for specific Doggerland stories. A winter camp used for generations on a promontory above a frozen river. A summer aggregation site near a fish run where multiple bands came together. Maybe even a place where people laid their dead deliberately generation after generation in a particular grove or on a particular rise. If those exist, and given what we know from comparable landscapes on land, it would be surprising if they didn't. Some of them may still be preserved almost intact in deep peat pockets, shielded from heavy trolling in channel fills that were quickly buried, and then left alone in hollows cut into glacial deposits that slumped and sealed soon after abandonment. What might those sites hold? Hearths with charcoal that still smells of heather when burned in a lab. Clusters of flint waste showing where someone sat and knapped tools. Organic remains that almost never survive on dry land. Wooden spears, woven mats, basketry, perhaps even worked bark or cordage. In waterlogged archaeology, things we think of as lost forever suddenly reappear. Footprints pressed into old mud, the poles of fish traps, the planks of simple walkways across boggy ground. Doggerland had bogs and wet meadows and tidal creeks before the sea. There is a real possibility that somewhere out there under 5 or 10 meters of water and a veil of sand lies the Mesolithic equivalent of a boardwalk. A line of stakes or a corduroy surface where people trod day after day across the wet ground. On land, we found such trackways in places like Denmark, Ireland, and the Somerset levels in England. Under the North Sea, the same conditions that make bog bodies possible could have preserved wooden structures from a time when Britain and the continent were still one. If we ever find one of those submerged trackways and can follow it, where does it lead? To a seasonal hut ring, a cluster of houses on slightly higher ground, a small platform used for fishing and ritual. Every plank and post would carry tree ring patterns that could be matched to other timber, revealing felling seasons, building episodes, even climate variations year by year. But as the picture sharpens, another question looms larger. Whose past is this? Doggerland doesn't belong neatly to any one modern nation. Its fragments lie in the exclusive economic zones of the UK, the Netherlands, Germany, Denmark, Belgium, even Norway further north. Artifacts brought up by fishermen might land in Dutch harbours, British harbours, German harbours, sometimes with no precise coordinates. The bones themselves, when analysed, often turn out to be the ancestors of nobody and everybody, people whose descendants merged and divided and moved in so many waves that no modern population can straightforwardly claim them as ours. Law, however, likes clear ownership. Right now, most submerged prehistoric material in the North Sea is managed through a patchwork of national heritage laws, international conventions, and project-specific agreements. Some countries treat finds under a certain depth as automatically protected cultural heritage. Others focus more on shipwrecks and leave older buried landscapes in a grey zone. Commercial operators are often required to avoid known sites and report significant fines. But significant is not always defined, and enforcement can be patchy as the chances of finding intact Doggerland sites improve. These questions become less theoretical. If a power cable survey reveals a dense scatter of hearths, post holes, and human remains on the seabed, who has the right or the responsibility to decide what happens next? Do we excavate knowing that underwater archaeology is expensive and inevitably destructive? Do we protect in place even if that means rooting a multi-billion project? If fishermen are the first to recover human bones, are those bones scientific specimens, ancestral remains, or both? Who speaks for the people who lived and died there? There are no easy answers. Some argue that submerged landscapes like Doggerland should be treated as a shared European heritage managed cooperatively across borders. Others emphasize local stewardship. Dutch bones in Dutch museums, British bones in British labs. Indigenous groups in other parts of the world have pushed hard, sometimes successfully, for control over ancestral remains and sacred sites, reshaping how archaeologists handle human material. While Doggerland's communities don't have obvious living descendant groups making claims in the same way, the ethical questions echo respect, consent, the difference between curiosity and exploitation. Layered on top of that is another uncomfortable parallel. As we reconstruct a world that drowned, we're living through our own slower version of the same story. Around the globe today, low-lying coasts are eroding, wetlands are retreating, and entire communities are facing relocation as sea levels rise and storms intensify. Villages in Alaska list into thawing permafrost. Islands in the Pacific sea saltwater creep into groundwater. Even around the North Sea itself, coastal defenses are being raised and retreated, and managed realignment schemes are deliberately giving certain land back to the tide. Doggerland's fate is not a distant exotic tragedy. It is a mirror tilted slightly back in time. When we map an ancient shoreline 30 kilometers out from today's coast and say here people fished, we are implicitly saying that the line we now call land is temporary, that modern harbors and CIU walls and hull towns are perched on the same kind of shifting edge the Doggerland people once occupied. That in a few thousand years, maybe sooner if we mishandle our climate, the archaeological maps of the future might show another drowned plain under some future sea with our cities reduced to ghostly lumps in the sediment. That's one reason the story of bones in nets feels urgent now. It's not just about solving an archaeological puzzle. It's about watching in slow motion and with better instruments. What happens when a world goes underwater? How people cluster on higher ground, how they adapt, how long they hold on before retreating or before the sea takes the decision away from them. As our tools improve, we're likely to see all of this much more clearly. We may find not just isolated camps, but networks of sites tracing human movement upslope as the shoreline advanced generation by generation. We may identify particular valleys where people stayed until the last possible moment, then left behind hurriedly abandoned hearths and lost tools in their wake. We may even be able to say with some precision, this community vanished from the record within a lifetime of the sea reaching this level. And then we'll have to decide what to do with that knowledge. Do we treat Doggerland simply as a lost country to be catalogued and displayed, another curiosity in the long human story? Or do we see it as a warning written in mud and peat, a reminder that the ground under our feet is never as permanent as it feels? As we move into the last part of this story, there's one question that hangs over everything we've uncovered so far. When you stand on a familiar beach today and look out over those waves, what exactly are you looking at? A distant, unreachable past, or the edge of a world that is already beginning to look a lot like Doggerland once did? When you stand on that beach and look out, you're not just looking at the sea. You're looking at layers. Nearest to you is the present. Storm waves, shipping lanes, turbines turning on the horizon, trollers dragging nets the way they've done for generations. Beneath that is the working sea of charts and economics, depth soundings and cable routes and fishing quotas. Beneath that again are the maps the geologists see. Buried rivers, drowned dunes, ancient shorelines. And then at the very bottom there's a layer that still feels almost impossible to grasp. A living country, not a mythic Atlantis with marble temples and crystal towers. A country of red beds and older car, of low sandy islands and tidal creeks. A place where red deer browsed along the margins of willow thickets, where people knelt to straighten fish on racks of hazel and ash, where children chased each other up the same little knoll above the marsh for generations. For most of its existence, Doggerland wasn't doing anything special. It was just being land. Seasons turning, rivers meandering, lakes silting in, people adapting. The drama came at the end, and even that was mostly slow. That's the part that's easy to forget when we talk about a lost world. The North Sea didn't leap into existence one morning. It rose like a very patient, implacable tide. A few millimeters a year on average, a little more during meltwater pulses, a little less during brief, colder snaps. Some years the sea barely noticed. Some years a winter storm clawed a new channel through a sand ridge and never quite gave it back. From shore level, the story would have looked more like negotiation than catastrophe. Move the camp a bit higher this year. Rebuild the fish traps where the current is better. Cut new stakes because the old ones are waterlogged. Visit the cousins inland a little more often because the good grazing is shifting. Every now and then, though, the negotiation failed. A storm surge overtopped a low barrier and didn't drain away as expected. A winter flood chewed through a levee of peat and tree roots. A river changed course permanently, leaving a beloved lakeshore stranded as a sodden hollow, while a new estuary opened in what had been safe ground. And rarely something on the scale of Storegga sent walls of water tearing across the shallows, turning negotiation into flight. Those are the moments that catch our imagination because they leave marks that feel almost cinematic. Layers of coarse sand dumped abruptly over pets. Whole forests drowned in situ. Trunks still rooted but smothered in silt. They make good headlines. Mega tsunami destroys Stone Age paradise. But the bones in the nets, the spear points in the dredges, the peat from vanished marshes tell a quieter story at least as important. People stayed as long as they could. They rebuilt. They learned the shapes of new channels and sandbanks. They moved camp, then moved it again, then moved it for the last time when there was nowhere left to go. All of that, the everyday stubbornness and the sudden endings, is still there, layered into the seabed. Some of it we understand fairly well. The broad outline of post-glacial sea level rise is one of the best studied curves in quantitative science. The submerged river systems are mapped with enough accuracy that we can trace their courses like veins on the back of a hand. Radiocarbon dates from peak beds, drowned forests and bones give us anchors in time. We can say with reasonable confidence when certain areas went from dry to tidal, from tidal to fully marine. We can also say that people were present through most of that story. The stone tools, butchered animal bones, hearth traces, and now human remains themselves make that very hard to doubt. This wasn't an empty stage waiting for the water to come in. It was occupied. Other things are much less certain, and it's important to keep them in the maybe column. Was Doggerland densely populated, or was it a network of small shifting micro-territories used by scattered bands? Were there long-lasting base camps that persisted for centuries? Or did people favor short-lived, lightly built sites that came and went with the seasons? Did they treat particular places as special burial grounds, ritual loses, meeting points? Or were meanings attached more to routes and movements than to fixed spots? We have hints, clusters of finds along certain paleo shorelines, human bones pulled from peat that may once have been formal burials, concentrations of tools near river junctions. But a handful of finds and a few cores do not yet add up to a full social map. Different researchers model different population densities, different degrees of mobility, different responses to encroaching water. Some emphasize continuity, Dogon people as the straight-line ancestors of later Neolithic groups on today's coasts. Others suggest a more braided pattern of movement and replacement. Even the famous Storegga Tsunami is in its details a live debate rather than a solved mystery. There's strong evidence that it sent waves across the North Atlantic and into the North Sea. There are clear tsunami deposits in some estuaries, but how far inland did those waves reach? How much of the remaining Doggerland plain did they inundate, and how long did the damage last? Did communities abandon low-lying areas en masse? Or did they return and rebuild much as people do after floods today? You will see confident diagrams online showing Doggerland before Storegga and Doggerland after Storegga, as if a single day redrew the map permanently. The real story is very likely messier, a big shock event layered on top of an already vulnerable changing coastline with different regions and communities affected in different ways. That uncertainty isn't a failure. It's what you'd expect when you're trying to read human lives out of mud, sand and bone fragments scattered and reworked by centuries of trolling and tide. And it's changing fast. Every new survey grid, every drilled core, every bit of environmental DNA adds another pixel to the picture. A century ago, Dogon wasn't even a word. A few decades ago, it was a contour on a paleogeographic map. Now it's close to becoming a textured landscape in which we can say here was a marsh edge with hazel scrub and elk, here a tidal creek full of flatfish, here almost certainly a place people used again and again. That's the image I want to leave you with when you next see the North Sea. Not a flat, opaque sheet of grey water, but a kind of horizontal archive. Imagine the seabed as shelves stacked on top of each other. On the top shelf, wrecks of medieval cogs and Napoleonic warships, lost nets, modern debris. On the shelf below, Roman and Iron Age river channels, Bronze Age fishing grounds, trackways that once crossed tidal flats. Below that, the Mesolithic plains with their buried hearths and post holes and footprints. Beneath that again, glacial outwash channels and the scars of ice sheets. Between those layers run threads, the same valleys used and reused, the same high spots chosen for camps and signal fires and lighthouses and wind turbines, the same human impulse to edge up against the water and say, "Here, we'll live here, we can make this work." When a fisherman hauls up a human jaw or a piece of antlines carved into a harpoon, they're not pulling up a random relic. They're tugging on one of those threads. For a moment, the shelves line up. The person who dropped that tool or laid that body on the ground is closer than they've been in thousands of years. Most of their world is gone. The smells, the sounds, the particular light of dawn over those vanished marshes, but not everything has vanished. Some of it is locked in peat and silt, in DNA fragments and tree ring patterns, and subtle changes in grain orientation on flint. Enough potentially to reconstruct parts of a country that no one has seen in 8,000 years. Over the coming decades, if we choose to look carefully, Dogon might go from an outline on a scientist's slide to one of the best understood prehistoric landscapes on Earth. Not because it's magically preserved, but because we happen to be flooding it with sensors and sampling it constantly for our own 21st century reasons. Energy grids, fiber optic cables, safer shipping routes. In trying to secure our own future on these coasts, we're accidentally illuminating the past of people who walked here when those coasts were far to the west. If you've stayed with this story all the way to this point, you're part of that process too. Curiosity is what makes it worthwhile to spend the time, money, and intellectual effort to tease meaning out of mud. If you'd like to help more people discover this kind of deep-time detective work, take a moment now to like this video, subscribe to the channel, and leave a comment. It really does tell the algorithm that this sort of slow, careful history is worth sharing. And since Dogland was once a bridge between places, I'd love to see where you're listening from now. Drop a comment with your country or city, and what time it is where you are as you're watching. Are you on a coast, inland, maybe even near the modern North Sea next time you see the North Sea on a map, or fly over that churned grey surface in a plane? Try this. Imagine the water draining away like bath water, revealing valley after valley, island after island, tracks and hearths and forest stumps, emerging inch by inch. Picture people standing there backlit by a low sun, watching the tide for fish or the sky for weather, with no idea that one day someone would be squinting through sonar and sediment trying to find them again. They're gone, but they're not entirely lost. They're still there under familiar waves, waiting for us to learn how to listen properly to the bones in the nets and the whispers in the mud. If you enjoyed traveling through deep time with me, there's more to come. Tap like, leave a comment, and subscribe to stay with us on the journey. And before you go, tell me, where are you in the world, and what time is it as you listen? And yet, even as we argue about wave heights and run-up distances, we're learning to read these events in finer and finer detail. The same techniques that model a prehistoric tsunami across a half-drowned plain can also do something else. They can help us reconstruct that plain itself. Because to understand how the wave moved, you have to know what it moved over. That requirement is driving a new kind of mapping of the North Sea floor. One that is starting to reveal Dogland's buried hills, rivers and coasts with startling clarity. If you want to find a lost country under a shallow, murky sea, you can't just look down. Light doesn't penetrate far. And even if it did, you'd only see the modern seabed. Ripples, sand waves, troll scars. Doggerland is not lying there, intact, waiting to be photographed. It's buried. So researchers had to learn to see with something else. They started using sound. In seismic reflection surveys, a ship tows an array of sound sources and receivers across the water. Short, controlled bursts of energy are fired downward. That sound travels through the water, hits the seabed, and then keeps going into the layers beneath. Every time it passes from one kind of material into another, from soft mud into compacted sand, from sand into ancient peat, part of the wave bounces back toward the surface where it is recorded. Each ping is just a faint squiggle of returning energy. But string millions of them together along a line, and you get a cross-section through the subsurface, a kind of acoustic X-ray. Stack many such lines side by side and stitch them into a 3D volume, and you can scroll through the buried landscape as if you were flying above it with the water drained away. Oil and gas companies did exactly this from the 1960s onwards, not because they cared about drowned human landscapes, but because they were hunting reservoirs. To them, the key things were deep structures, tilted blocks of a rock, folded layers, traps for hydrocarbons. But their data sets captured everything in between the seafloor and those deeper targets, including the last few tens of meters where Doggerland's story is written. When archaeologists and geologists later got access to this seismic archive, they discovered that those shallow layers were full of pattern. Parallel smooth reflectors that once were lake bottoms, irregular incised shapes that cut down into older strata, ancient river valleys, packages of inclined layers that pinch out toward the sea, former shorelines, barrier bars and deltas. In some volumes you can trace meandering channels snaking from what used to be the British rivers eastward toward the continent, their paths frozen in mud long after the rivers themselves drowned. On a seismic slice, a buried river is not a blue curving line. It's a lens-shaped erosional cut filled with younger sediments bounded by sharp contacts. Several such channels can braid together, split apart and rejoin, building something that looks suspiciously like a continental river network laid across the modern seabed. Stitch those together in map view, and you get ghost drainages, the old Thames routing northeast and joining rivers from what is now the Rhine and Meuse, smaller tributaries heading in from the former Scottish rivers, low interludes in between. You can even see where coastlines once lay. In some places, the seismic reflections climb gently upward and then stop abruptly at a surface that slopes seaward. That's the buried edge of a coastal cliff or beach ridge. In others, you see stacked wedge-shaped bodies of sediment that thin landward and thicken offshore. Prograding shore faces built by waves chewing at a shoreline that was slowly retreating under rising seas. By themselves, these are shapes, geometry. You can tell where the highs and lows were, where rivers cut, and where banks stood. But you don't yet know when any particular feature was active, or exactly what kind of environment it hosted. For that, you need to trade sound for mud. Enter sediment cores. A core is at heart just a narrow cylinder of seabeds stabbed and pulled out of the subsurface. But if seismic surveys are like MRI scans of the whole body, a core is more like a biopsy. Local, detailed, textural. Lower a corona to the seabed, drive it down with weight or a triggered piston, pull it back up, slice it open. And suddenly you're looking at a vertical column of history compressed into a few meters. In that column, the layers stack like pages of a book. Coarse sands at the bottom might mark an old river channel, fast water, high energy. Above that, a transition in silts and clays suggests a slowing current, perhaps a floodplain or a tidal flat. Then a dark fibrous layer, peat. That's a smoking gun for land at or just above sea level with vegetation growing in waterlogged soils. Leave that peat in place long enough and roots, leaves and tiny woody fragments accumulate, trapping pollen, spores and insect remains. Cap it with marine muds or sands full of shell fragments, and you're looking at the moment the sea rolled in. To read that story, scientists unspool each core by core. They log the visible changes in color and grain size. They scan it with X-rays and geochemical sensors. They take subsamples, break them down in the lab, and look for clues too small to see with the naked eye. Peat, for example, is not just peat. Under the microscope, it may contain pollen from different kinds of trees and grasses, each with its own ecological preferences. Grains of pine pollen, oak, hazel, alder, sedges, heathers. The proportions of each shift subtly through time as climate and local hydrology change. Layer by layer, that pollen rain records what the surrounding vegetation looked like when the peat formed. In some cores from the southern North Sea, lower pets preserve pollen assemblages dominated by cold-tolerant grasses and herbs. Open steppe or tundra conditions near the end of the last ice age. Higher up, those give way to mixes that indicate birch and pine scrub. Then mixed deciduous woodland as the climate warmed and trees colonized the plain. In between, pulses of wetter indicators, alder, sedge, swamp plants flag the expansion of wetlands and boggy hollows. These shifts give you a rough climate curve and a sense of what Doggerland's habitats looked like at different times. Open grazing grounds, wooded ridges, marshy valley bottoms. Insects add another layer of resolution. Their remains, bits of beetle shells, fly parts, tiny jaws are often exquisitely preserved in waterlogged sediments. Different beetle species are picky about their environments. Some like cool, open, windswept ground. Others prefer damp woodland. Others still only live in salt marshes or on the margins of freshwater ponds. By identifying which species show up in each layer, entomologists can reconstruct not just temperature and humidity, but specifics like shallow vegetated pools with fluctuating water levels or brackish marsh subject to occasional marine flooding. Microsills from the aquatic world play the same. Datums, silica-shelled algae, change community composition along salinity and nutrient gradients. Foraminifera, tiny shelled protozoa have species that prefer normal marine conditions and others that tolerate brackish or even nearly fresh water. Pick them out from each sediment layer and you can see the moment a freshwater lake became an estuary or a tidal flat became open coast. When a core cuts through a peat that suddenly gives way to a thin sheet of clean sand packed with marine microfossils, that boundary is telling you something very specific. At that spot, solid ground was abruptly drowned or overrun by the sea. Whether that was slow encroachment, a storm surge, or a tsunami is another question. But the basic sequence, land surface, then marine deposit, is clear. Now, take dozens of these cores scattered across the North Sea. Tie each one to a position in the seismic volume. Date the organic bits in them with radiocarbon or other techniques. Align those ages with global sea level curves and regional climate records. What you end up with is not just a flat "there was land here once" map, but a time-sliced reconstruction. This river was active around 12,000 years ago. This peat bog formed between 9,500 and 9,000 years ago. This shoreline retreated through this corridor by 8,500. From those building blocks, researchers construct digital terrain models of Doggerland. 3D surfaces of the buried topography draped with reconstructions of vegetation and water bodies. These models start with modern bathymetry, how deep the sea is today, then subtract estimated amounts of sediment that have accumulated since drowning, then adjust for post-glacial rebound and subsidence, then integrate the shallow architecture revealed by seismic lines, cause anchor the elevations and, crucially, the timing. Feed in an estimate of global sea level at a given date, and you can ask the model a simple question. Which parts of this landscape would have been dry land then? Where were the rivers, the lakes, the marshes, the islands? Change the date and watch coastlines march inland, rivers back up into estuaries. Interflows become peninsulas. Peninsulas pinch into islands and finally disappear altogether. These are not static pictures. There are hypotheses you can test. Want to see how a particular Doggerland river might have behaved as sea level rose? Run a hydrometeorological model across that reconstructed topography. Does water concentrate into a single channel or split into a braided delta? Are there spots where flooding would likely have created persistent wetlands good for reeds, birds, fish? Where are the crossings shallow enough for people on foot? Where do potential settlement sites cluster? Near freshwater, on slightly higher ridges close to resource-rich ecotons. The same digital Doggerland is used to test tsunami scenarios, storm surges, and the connectivity of human groups. If narrow land corridors remained between Britain and the continent at a given time, how constricted were they? Could herds migrate seasonally across them? Could humans? At what point does the model show Britain effectively cut off except by boat? Each run is an experiment in plausibility. The catch is that every input sea level curve, sediment thickness, amount of post-glacial warping, interpretation of seismic reflections comes with uncertainty. Change one parameter and the shape of late Doggerland shifts. A ridge that looks like safe high ground under one set of assumptions might be barely above spring tide in another. A channel that appears as a persistent river in one reconstruction might with slightly different dates already be a tidal creek. That's why these maps keep changing. The first widely publicized Doggerland maps in the 1990s and early 2000s showed a broad, almost continuous land bridge. A huge green plain stretching from what is now East Anglia across to Denmark with rivers neatly labeled, coastlines crisply drawn. As more seismic lines were added, those clean shapes broke down into finer detail. What looked like a smooth slope became a stair of terraces. What looked like a single channel resolved into multiple shifting paths. New cores pushed the timing of some pets earlier or later, forcing shoreline positions to move. Each new dataset nudges the picture. A high-resolution seismic survey commissioned for a wind farm might reveal previously unmapped channel carving through what had been assumed to be a stable plateau. Suddenly, that plateau is narrower, perhaps broken into two islands, changing how we imagine people moving through the region. A core from a high spot might unexpectedly hit marine sands immediately below a thin veneer of modern sediment with no peat at all. That suggests that by the time peat was forming elsewhere, this particular ridge was already underwater. The map is adjusted again. These revisions aren't failures. They're the normal process of turning a very sparse, patchy archive into a coherent narrative. Doggerland was real ground experienced in excruciating detail by the people who lived there. Every knoll, every muddy hollow, every shortcut through the reeds. Our reconstructions reduce that complexity to pixels and contour lines, and those pixels shift as the evidence improves. In one sense, this can be frustrating. There is no final definitive map of Doggerland to print and call complete. In another sense, it's liberating. It means the lost country is not a single frozen idea, but a space of possibilities that science is steadily narrowing. With each seismic cube examined, each core pulled up, each pollen diagram plotted, the error bars around that drowned landscape shrink. We may never know exactly where a particular camp stood or which dry ridge a particular family called home. But we can say with growing confidence that there were ridges, that there were camps, that the rivers we trace in sound and mud are the same ones people once followed with their feet. And we can start carefully to look beyond the bare bones of topography and ask in that evolving map, where do the traces of everyday life cluster? Where under the waves should we expect the artifacts, the hearths, the art, and the tools of Doggerland's people to lie? When archaeologists go looking for those traces, they are not expecting golden crowns or stone temples. The toolkit of Doggerland, as far as we can see it, is almost aggressively ordinary, and yet, in its ordinariness, it is incredibly revealing. Most of what turns up from the North Sea, whether dragged in nets, sucked up in aggregate dredges, or recovered from intertidal peat on the modern coasts, is small, hard, and tough enough to survive thousands of years of burial and a few rough encounters with machinery. Worked flints, that's the headline act. To the untrained eye, a lump of flint looks like, well, a lump of flint. But experienced eyes see geometry, striking platforms, bulbs of percussion, carefully prepared edges. The North Sea has given up thousands of these pieces over the decades, many of them rolled and battered by waves and dredges, but still recognizably human-made. Blades and bladelets, flakes with retouch along one edge, tanged points that once tipped arrows or light spears, scrapers with a telltale steep continuous edge used to work hides, barnins, chisel-like tools used for engraving or working bone and antler. Alongside the flint are organic tools, rarer only because they rot more easily. Antler picks, for example, sections of deer antler with their tines chopped off or modified, bases battered and pitted from hard use. Very similar tools are known from early Mesolithic sites on land where they were used to dig pits, extract flint nodules, and work in wet, muddy ground. Harpoon points made of antler or bone carved into barbed, elongated shapes. Some have one row of barbs along one side. Others have double rows, creating fearsome fish and seal catching devices. A few are broken where the tang would have fitted into a shaft, sheared in some long-forgotten struggle with a large animal or a snag on the riverbed. Then there are the quieter traces, polished or striated patches on waterlogged wood that look suspiciously like the scars of stone adzes, stakes driven into channel margins and then buried by later sediments, charcoal lenses and fire-cracked stones in cores that happen to hit old camp surfaces or hearths. These are not museum pieces. They are the industrial rubbish of a hunter-gatherer economy. The power of these scraps lies in how much they can say once you start to look at them closely. Take a simple flint scraper. Under low magnification, the sharp edge might show a bright, glossy polish. On one tool, that polish is smooth and domed, extending slightly back from the edge with fine parallel microstriations at right angles to the edge. Experiments with replica tools tell us this combination is typical of hide working, especially dry hide scraped repeatedly in one direction to remove fattened flesh and soften the skin. On another scraper, the polish might be duller with more granular texture and striations running along the edge instead of across it. That pattern tends to show up when tools are used on plant materials, cutting reeds, shaping wooden shafts, processing roots or tubers. Microscopic use-wear analysis like this has been applied to numerous Mesolithic assemblages from around the North Sea coasts. Even when we can't be entirely certain that a particular piece was found offshore rather than near it, the pattern is consistent. Lots of hide working, lots of woodworking, plenty of cutting and scraping plant matter, regular but more limited direct traces of butchery and hunting. That doesn't mean people hunted rarely. Spears and arrows, after all, don't usually come back with convenient animal bloodstains for us to detect 8,000 years later. Projectiles and butchery knives might be curated and resharpened over and over, leaving complex overlapping wear that is harder to interpret. What the clearer signals tell us is that a huge amount of time and effort went into everything around the hunt. Preparing skins for clothing and shelters, processing plant fibers and reeds, shaping wooden tools, mending gear. Plant processing is particularly interesting in the context of Doggerland. Some tools from the broader region show were consistent with working silica grasses and perhaps cereals, polishes that experimental archaeologists often associate with cutting wild grains. Combine that with pollen evidence for expanding grasslands and wetland plants on the plains, and a picture emerges of people who are not just chasing big game, but also exploiting a rich spectrum of plant resources. They may have been harvesting and stockpiling seeds, collecting edible roots and bulbs from marshes, weaving baskets and mats from reeds growing in floodplain ponds. Harpoon points and barbed antler pieces add another layer. Their styles change through time and vary between regions, hinting at different fishing traditions along rivers and coasts. Some are robust, suited for large fish or marine mammals. Others are slender with many small barbs, ideal for spearing salmon or eel-like fish in shallower waters. Wear and breakage patterns, snapped tangs, barbs smoothed by friction, suggest repeated use, retrieval, repair. In a drowned landscape full of channels, inlets and shallow lagoons, such gear would have been central to survival. Many of these tools come to us as orphans. A beam troll scrapes up a handful of flints from somewhere on the seabed. A dredger pulls a few antler pieces from a gravel bank. The precise original context, was it a campsite? A kill site, a riverside working area, is stripped away. Archaeologists prefer finds that are in situ, undisturbed, where the relationships between artifacts, sediments, and echoquettes can be read like sentences in a text. Dogland rarely gives us that luxury. And yet, even isolated finds have impact. A single tanned point with an unmistakably early style can extend the known range of a particular culture or hunting tradition hundreds of kilometers into what is now open water. A unique antler artifact with engraved lines or a possible decorated object can hint at symbolic behavior on the drowned plain, even if every other scrap from that spot is gone. A human-modified timber with clean-cut marks and a possible mortise can suggest woodworking skills beyond ad hoc shaping of branches. Perhaps the building of fishes, platforms or more elaborate structures. These high-impact pieces are rare, and interpretations around them are necessarily cautious, but they function like bright pins on an otherwise grey map, forcing reconstructions to expand if a particular type of harpoon is found in Danish waters, and the same type appears in Dutch-landed dredge spoil that implies some level of cultural continuity or contact along the intervening lands. If a style of microlith known from coastal Belgium also shows up far offshore, then people carrying that toolkit were exploiting the interior of Dogland, not just skirting its edges. One way to make sense of this patchy scatter is to think about where activities would have naturally concentrated. On dry land, Mesolithic sites often cluster near water, lake edges, river terraces, springheads, sheltered coves. These are places where resources converge. Fish and birds, drinking water, good reeds, game trails, and often navigable routes through the landscape. In a low relift plain like Doggerland, that tendency would likely be amplified. Slight rises along major rivers would have offered safe, dry ground not far from rich wetlands. River mouths and estuaries inlets would have been hotspots, shifting zones of fresh and salt water rich in fish, shellfish, birds, and driftwood. Now overlay that behavioral tendency onto the reconstructed maps from seismic and cores. Ancient river channels show up clearly in the subsurface. The confluences, levees, and abandoned meanders can be mapped where those features intersect with evidence for pets and stable land surfaces at the right dates. Archaeologists mark prime targets, likely corridors of movement, likely locations of repeated camps, likely spots where activity and discard rates were high enough that more artifacts should be buried. Shorelines are another magnet. Beaches and barrier spits concentrate certain kinds of resources: shellfish beds, stranded whales, seaweed, stones, and offer flat open spaces for gatherings. Mesolithic shell mittens along modern coasts are classic examples of such focused use, but whether similar piles existed on Dogland shores is still an open question. Shells do not always preserve well in acidic pets, and storm and tide action reworks them. If they are there, they are harder to see in cores than in a cut cliff on land. Even so, some offshore cores have turned up layers rich in shell fragments and burned material sandwiched between pets and sands. Possible hints that coastal living left its mark between rivers, shorelines, and small lakes. The drowned plain would have been speckled with zones of intense repeated use, separated by larger stretches of land that people mostly just passed through. The artifacts we recover today almost certainly come disproportionately from those focal areas, not from every square kilometer of the former country. That matters when you read the evidence. A cluster of flints and antler points in one core is not proof that all of Dogland was a crowded, continuous settlement. It might just mean you've stabbed into one of the busiest spots on a mostly quiet map. All of this makes the line between reconstruction and romanticism very thin. It is tempting when you hold a beautifully retouched flint blade that came from under 30 meters of water to imagine the person who last gripped it. Maybe they were standing on a riverbank at dawn, damp mist rising from the water, using that tool to slice strips of meat or trim a newly carved spear. Perhaps they dropped it, cursed, and left it lost between the roots of a tree that has long since rotted away. Scale that moment up by thousands of artifacts and thousands of years. and you start to see villages, markets, even a kind of North Sea Atlantis bustling with life. But the hard evidence doesn't yet support that kind of elaborate storytelling. What we can say with decent confidence is more modest and more interesting. We have worked flints that match known mythic traditions from surrounding lands. We have antler picks and harpoons that fit into a broader pattern of hunter-fisher-forager lifeways in northwest Europe. We have microscopic wear traces that point to a mixed economy of hunting, fishing, plant gathering, hide and woodwork. We have a growing sense that river corridors and shorelines were the main arteries of this drowned landscape, focusing activity and leaving more artifacts behind. We do not have yet in situ houses laid out in neat rows on the seabed or carved figurines sitting exactly where they were placed. We do not have clear evidence for monumental structures or dense permanent settlements out on the plain. Ideas about temples, sophisticated agriculture, or a unified Dogon culture with shared governance are at this point speculation. That doesn't mean Dogon was dull. On the contrary, the very ordinariness of its artifact record, stone tools, antler, harpoons, worked wood is what makes it remarkable. It ties this vanished country directly into the known world of Mesolithic Europe rather than separating it as some mythic lost civilization. The people who lived there were doing the same sorts of things their contemporaries were doing on what is now dry land. Exploiting ecotones, tinkering with tools, inventing local variants, passing skills and styles down generations. Where we can allow ourselves a little imagination is in filling in the everyday gaps that the tools point toward but cannot fully show. A cluster of hide working scrapers implies skins being stretched on frames, smoked over hearths, sewn into clothing. Plant-polished blades imply baskets, fish traps, sleeping mats, cordage. Harpoons imply boats, simple dugout canoes or rafts slipping quietly along backwaters, children learning to balance, adults reading currents by eye. As long as we mark clearly where evidence ends and inference begins, these reconstructions can be useful, even necessary. They help us remember that Doggerland was not an abstract bathymetric contour on a map, but a lived space. A place where every flint flake and antlerless splinter was part of someone's solution to the problem of staying alive in a changing world. Staying within those careful boundaries matters for another reason too. The more Dogland captures public imagination, the more stories accumulate around it about advanced lost peoples, forgotten cataclysms, even pseudo-historical claims tying it to later myths. Against that backdrop, the humble reality of scrapers, harpoons, and woodworking traces can feel underwhelming. But it is precisely those humble pieces grounded in mud and wear patterns and stratigraphy that anchor the story in the real, and they set up the next question. If this toolkit, this way of life was spread across a lowland the size of a small country, with people following its rivers and coasts for millennia, what does that say about Dogland itself? Was it truly a coherent country in any meaningful sense, or just a large changing patch of ground stitched together by seasonal movements and loose networks of kin? To answer that, we have to zoom out again. From individual blades and barbs to the scale of populations and paths across the plain. So, was it really an entire country? It depends what you mean by country. If you zoom out to the cold bathymetric map view, then yes. For long stretches of the last ice age and the early Holocene, the area we call Dogland really did form a continuous expanse of dry land, not a scattering of islands. At its maximum around the end of the last glacial period, we're talking about a lowland that stretched from what is now eastern England all the way to the coasts of the Netherlands, Germany, and Denmark. Estimates vary, but at its largest, that landscape may have covered well over 100,000 kilometers, bigger than modern Scotland, roughly on the scale of a small European country. But it didn't stay that big or that simple. Sea level didn't suddenly jump from Landbridge to North Sea in one go. It crept over thousands of years. The shoreline nudged inland, then stalled, then surged again in pulses as ice sheets melted and distant ice dams failed. What started as a broad, mostly flat plain became a dissected mosaic. First, there were wide river valleys inside into the lowland, draining meltwater from the north and rain from the south. Then Estes widened back, flooding into those valleys. Lakes formed in shallow hollows. Low ridges and hills became peninsulas. Eventually only higher patches like the Dogger Bank itself remained as islands before even they were swallowed. So when people talk about Dogland as if it were one fixed place, that's already a simplification. The dry ground under the modern North Sea was never a single stable platform. Its shape, size, and habitability changed over and over as coastlines migrated, rivers shifted, and local conditions swung between tundra, steppe, forest, wetland, and finally sea. In that sense, calling it a country is a metaphor. It's a way of giving a human scale to a drowned region whose borders and character were always in motion. Think about what country means in the modern world. It implies a boundary line on a map, a government, a flag, maybe a shared identity and language. None of that existed for Doggerland. There were no customs posts on its ancient rivers, no capital city out on the banks of some vanished estuary. The people who lived there were small bands of hunter-fisher foragers, not citizens of a centralized state. But the metaphor isn't completely wrong either, because if you step away from political borders and think in terms of regions, places defined by shared environmental patterns and networks of movement, then Doggerland starts to look a bit more like a coherent country and less like a random patch of mud. For much of the late glacial and early Holocene, that land was the land route tying together areas that are now separated by water. If you walked north out of what is now the Netherlands, you wouldn't hit a sea. You'd cross river plains and marshes, maybe skirt some lakes, and eventually on the horizon low hills that would one day be eastern England. If you followed the great rivers northeast from what is now Germany, you could keep going into what is now southern Denmark without ever seeing open ocean. The plain was a hinge, a connector, a wide, relatively gentle corridor along which animals and people could move seasonally or over generations. From that perspective, the idea of a unified Dogon culture starts to feel less necessary than the idea of a Dogon network. Archaeology around the modern shores already hints at this. Mesolithic sites in Britain, northern France, Belgium, the Netherlands, northern Germany, and Denmark show tool types and traditions that overlap, diverge, then overlap again through time. Microlith styles, harpoon shapes, antler picks. Some types cluster in particular regions, others spread over enormous distances. When we see the same kind of tanned point off the Dutch coast and in Danish waters, or a similar harpoon style on opposite sides of the present North Sea, that's a strong sign that people, or at least their ideas, were moving across the intervening lands. But that doesn't mean everybody out there was the same. Stretch this story over thousands of years, and the plain ceases to be a single place and becomes a sequence of related but distinct landscapes. At the very end of the Ice Age, it was a cold open steppe scattered with wind-blasted shrubs and hardy grasses, maybe used by reindeer and the people who followed them. As the climate warmed, birch and then pine and hazel crept in. Marshes thickened, rivers meandered, shorelines wandered. Local conditions in one part of the plain might diverge sharply from another. Culture tends to follow suit. Give small bands of people a few hundred years in slightly different environments with slightly different neighbors, and they begin to drift. Tool traditions fork. Preferred hunting targets change. Stories and rituals take on local flavor. So rather than picturing Doggerland as one Mesolithic nation, it may be more accurate to imagine layers and pockets of cultural diversity spread across it. Along a major river, a group might develop distinctive fishing gear, particular harpoon forms, preferred ways of building fish traps, because they spend half their lives working that river's channels and lagoons. West toward the then coastline, another group might lean more heavily on sea mammals and shore resources, developing its own boat-making tricks, its own way of carving paddles or shaping dugouts. Further inland, on slightly higher, drier ground, deer and boar hunting might dominate, and people might favor a slightly different mix of microliths, a different way of hafting tools, a different set of seasonal routines. Over a millennium or two, those practical differences can shade into cultural ones. Distinctive ornaments, particular ways of decorating a tool handle or incising lines on a piece of bone, small variations in how burials are arranged or how hearths are built and reused, different melodies in whatever we would recognize as song. Linguists can't reconstruct the languages of these people. Sound doesn't fossilize, and we're tens of thousands of years before the earliest written records. But if you have multiple groups living semi-independently across a region the size of a small country for many generations, dialect differences are almost inevitable. Maybe they use different words for the same river or for the same fish. Maybe their counting systems diverged slightly. Maybe they could still understand one another when they met at shared hunting grounds or along river junctions, but with noticeable accents and local terms that needed explanation. In that sense, Doggerland was less a single country and more like a linguistic and cultural patchwork draped over a shared geography. What ties the patchwork together? is connectivity. Rivers were the motorways of this drowned world. They aren't just blue lines on a map. They are spines of movement. Animals follow them. People follow the animals and the fish. Cores and seismic maps show these ancient channels cutting across the plain, their levees and floodplains likely lined with campsites and way stations. If you lived near one of the big rivers, you were plugged into a north-south artery that might carry news, spouses, tools and styles over long distances. The same was true for coastlines. As sea level rose and the outer parts of Doggerland began to flood, new inlets and estuaries opened, people working those brackish edges, harpooning fish, gathering shellfish, hunting waterfowl, would have had every reason to move up and down the shore to seek good halouts, to explore new bays. Ideas ride along with that motion. Marriage ties could stitch distant groups into loose alliances. A woman born on what is now the Dutch side of the plain might end up living with relatives near the future English coast, carrying her knowledge of a certain way of net-making or her preference for a particular harpoon style with her. A skilled flint knapper might travel to kin an arduous journey away because their region had better access to high-quality raw material. Over time, such journeys build faint but real threads across the map. Taken together, all these movements blur any neat boundary you might want to draw around a Dogon people. What we have instead is a dynamic system. Groups splitting and fusing, shifting ranges as coastlines creep, maintaining just enough contact to keep a broad family resemblance in tools and lifeways across a very wide space. That's where the popular lost homeland stories both resonate and mislead. They resonate because from the point of view of people actually living there, the plain would have been home in a very deep sense. If your grandparents and their grandparents had always camped on the same stretch of Levi each spring, if your origin myth spoke of a particular hill or lake as the place your people first emerged or met their totem animals, then yes, the land beneath the present North Sea would have been charged with meaning. When the waters finally rose high enough that favorite campsites were repeatedly flooded or a well-known crossing became unsafe, that loss would not have been abstract. It would have been personal. Across cultures, humans tell stories about lands lost to the sea, flood myths in Mesopotamia, tales of drowned cities along the coasts of Brittany and Wales, stories from indigenous communities where rising lakes or shifting rivers swallow ancestral places. It's not a stretch to imagine that as Doggerland shrank, people framed those changes in narrative terms. Perhaps they blamed spirits or a great animal or the transgression of a taboo. Perhaps they spoke of a time before the waters came or when the shore was farther out. That kind of memory can echo for a very long time, mutating as it goes. Where the lost homeland narrative misleads is when it turns this very human response into a story about a single unified nation-state with high civilization. Then sudden catastrophic obliteration. That's where Doggerland sometimes gets folded into myths of Atlantis in the North Sea, complete with imagined temple complexes and advanced agriculture wiped out overnight by a mega tsunami. The actual evidence paints a slower, messier, and arguably more profound picture. The drowning of Doggerland was not a single day of disaster. It was a long sequence of incremental losses punctuated by occasional dramatic events. Marshes that used to be seasonally flooded became permanently soggy. A channel that was once a ford became a swimming crossing, then impassable. A sheltered bay became an open estuary with tides too fierce for small boats. Some groups adjusted, developing better boats, shifting their seasonal rounds, hugging newly formed coasts. Others moved inland, tracking familiar animal migrations onto higher ground. Some probably faded out, their preferred patch of world fragmented beyond rescue. In that context, Doggerland is less Atlantis and more like the North Sea's version of what coastal peoples are still experiencing today in places like the Arctic. The Ganges Delta or Pacific Atolls, a homeland gradually reconfigured by rising water, forcing continuous negotiation between memory, attachment, and practical survival. So, was it an entire country? Geologically, for a long time, yes, a continuous lowland the size of a modern nation. Socially, not in the way we usually mean when we talk about countries today. It was a broad, shifting region threaded by rivers and coasts that linked future Britain, the Low Countries, northern Germany, and Denmark into a single permeable zone of movement and interaction. Over thousands of years, that zone hosted multiple local groups, surely speaking different dialects, following slightly different seasonal patterns, maintaining their own traditions, yet sharing enough knowledge and genes that we can still see the family resemblance in their tools and faintly in our DNA. If you need a label, You can think of Doggerland less as a lost country and more as a vanished heartland, a core land that bound together the edges of northwest Europe before the sea took over. And that raises an uncomfortable, fascinating point. If this heartland was so important, and if people used it for so long, why are we only seeing stray tools, scattered hearths, and occasional timbers? Where are the people themselves? Why, when trawlers drag their nets, do the bones that come up almost always belong to animals, with just the rare, troubling exception? To get at that, we have to follow the shoreline one more time, right to the moment when water and land were in brutal, direct competition, and when the first human skeletons began their long, dark journey into the seabed. To understand why human bones are still turning up in fishing nets, you have to flip your mental map of the North Sea. Don't think of it as a flat, drowned graveyard where everything sank once and then quietly stayed put. Think of it as a restless machine. The seabed out there is not still. It moves slowly, constantly, and sometimes violently. Tides drag huge masses of water back and forth twice a day. Storms rake the bottom with waves whose energy can reach tens of meters down. Fast-flowing currents run along the coasts and across banks, scouring some areas while dumping sand in others. Over time, those flows sculpt the seabed into giant ripples, sand waves that can be several meters high and march across the bottom at a walking pace over years or decades. If you could watch the North Sea floor in time-lapse, it wouldn't look like a static desert. It would look like a conveyor belt of sand slowly rolling over itself, burying and then re-exposing older layers again and again. That's the crucial point. The bones and tools from Doggerland weren't lying on the surface last week, waiting politely for a troll net. Most of them have been buried in sediments for thousands of years. Clays, silts and pets laid down in lakes, marshes, river channels, and early estuaries. Those layers can be surprisingly stable on human timescales, but they don't stay buried forever. When a migrating sand wave crosses an old peat bed or an ancient channel fill, it can peel away the upper cover and suddenly expose material that hasn't seen daylight since before the sea arrived. Imagine a Mesolithic campsite on a river levee. People die there or nearby. Maybe their bodies buried shallowly in soft ground. Maybe it's not buried at all, just left in the forest or marsh to be scattered by animals and slowly incorporated into the soil. Over centuries, the river shifts. The area becomes boggier. Peat starts to grow, sealing everything under oxygen-poor, acidic, waterlogged conditions. Then, much later, the sea floods in. More sediments accumulate above. For millennia, nothing much happens. Then currents strengthen in that part of the North Sea. A sand wave begins to migrate across the old valley, shaving away the protective blanket that's been sitting there since the early Holocene. A storm hits. Waves focus their energy on that little rise. A meter or two of mud vanishes. Suddenly, a patch of that old peat bed is naked. Bone that was entombed in darkness is now sitting in loose, eroding material at the surface. The next troll net that passes over has a chance of picking it up. That's one half of the story. Natural dynamics. The other half is industrial. For most of human history, nobody was stirring up the North Sea floor on purpose. Then in the last century and a half, we started treating it like a construction site and a quarry. Bottom troll fishing drags heavy gear, doors, beams, chains, rollers across the seabed to herd fish into nets. This doesn't just collect fish, it disturbs sediments. Each pass can cut furrows, break up compact layers, and redeposit material downslope. In areas that are traveled frequently, the top layer of the seabed is effectively being plowed on a regular basis. Aggregate dredging removes entire patches of sand and gravel for use in construction and beach nourishment. Pipelines and telecommunication cables need trenches cut. Offshore wind farms require foundations, anchors, and cable routes. Each of those projects involves surveys, core samples, and sometimes large-scale excavation. Put those things together and you get a strange alliance: a restless sea, industrial disturbance, and archaeology. When an engineering company plans a wind farm or a pipeline, they don't just go out and start digging. Modern regulations in the North Sea region usually require detailed geological surveys and geotechnical sampling. That means seismic lines, side-con sonar, magnetometer sweeps, and crucially cores. Narrow cylinders of seabed pulled up to the surface. Those cores read like a vertical diary. Sand over silt over peat over gravel, shell fragments, pollen, sometimes charcoal from ancient fires, sometimes flint, once in a while bone. So, while fishermen are the ones most likely to physically bring up the bones, Energy and telecom projects are often the first to identify the buried landscapes where those bones formed. An engineer might look at a core and see obstacle to be avoided. An archaeologist looks and sees a lake shore that probably had campsites along it 10,000 years ago. Then when a trawler happens to pass across the fringes of that same buried lakeshore, now partly exposed by sand erosion and partly scuffed by construction activity, the net has a far better chance of snagging a piece of that story. There's another reason so much old bone survives at all. It was lucky in its choice of grave. Not all sediments are equal when it comes to preservation. Freshwater pets and the fills of old channels can be remarkably kind to organic remains. Peat forms in waterlogged environments where plant material accumulates faster than it decays. Bogs, marshes, swampy woodland. The water is low in oxygen, often acidic and relatively stable. Under those conditions, bacteria that normally break down bone and collagen work much more slowly or not at all. That's why famous bog bodies from places like Denmark, Ireland, and northern Germany still have skin, hair, and stomach contents after 2,000 years or more. The North Sea's Doggerland pets are older and less glamorous than Toland man, but the basic chemistry is similar. A bone buried in the right kind of peat can sit there for 8 or 10,000 years and still be solid enough to survive a rough trip in a troll net. Ancient river channels are another key. When a river shifts course, it often leaves behind a filled-in meander loop or abandoned channel. Those features tend to collect fine sediment and organic debris in low-energy water. Again, a good recipe for preservation. Many of the human and animal remains recovered from the North Sea can be traced based on their position and the associated sediments to these old channel systems and adjacent petlands. So picture the chain of events that leads to bones in a net. A person dies on land. Their remains are incorporated into soil in a relatively calm, wet environment, a levee, a floodplain, a marsh. Over time, that place becomes a peat-fill hollow or a gentle slope into a slow channel. Sea level rises, floods it, and then blankets it with marine sediments. Currents and storms eventually erode some of that marine cover away, particularly in places where sand waves are on the move. Industrial activity may help disturb and loosen the surface. Then one day, a troll gear crosses the spot. The bones that have sat quiet for millennia are now tumbling in a net along with cod and sand and the occasional brick. At that point, what happens depends entirely on the person who empties the net. Fishermen, somewhat unintentionally, have become the first responders of North Sea prehistory. They are the ones who routinely drag up mammoth tusks, oxer horns, antler picks, and every so often a human skull fragment or four. Without them, we would know far less about Doggerland because systematic underwater excavations there are still rare and expensive. Over the past few decades, several countries around the North Sea have set up voluntary and sometimes semi-formal reporting systems. In the Netherlands, trawler crews bring unusual finds, big bones, worked flints, carved antler to local museums or university contacts. Some harbours have specific collection points where fishermen can drop off material. In the UK, the Portable Antiquities scheme mostly focuses on land, but maritime archaeologists and certain regional museums maintain direct relationships with fleets. Denmark, Germany, and Belgium have their own versions of this patchwork. The quality of information those finds carry depends on how they're handled. If a fisherman notes the approximate position where something came up, its depth and the type of gear used, an archaeologist can tie that object to a particular patch of seabed and the known geology there. A certain sand wave field, a mapped peat layer, a relic channel. That in turn lets researchers start reconstructing which kinds of drowned landscapes are most likely to produce human material. Without that context, a bone is still valuable. It can be dated, analyzed for diet and isotopes, compared anatomically to other finds. But it's like a page torn from a book with no clue which chapter it belonged to. That's the core difference between random finds and proper archaeological sites. A random find is an object removed from its context by chance. A troll caught human jaw with a few teeth left or a Neolithic axe blade polished to a glassy sheen tells us that people were out there at some point. It may tell us the rough age and even a few details of the person's life or skill level of the craftsperson who made the tool. But it doesn't by itself tell us where they lived, how they died, or what else surrounded them. A scientifically excavated site is the opposite. It's all about context. On land, that means grids, careful recording of every layer and feature. Underwater, It means remotely operated vehicles, controlled suction dredges, detailed mapping, and often slow, expensive work in poor visibility. Every artifact is logged with exact coordinates, depth, and sediment description. Bones are left in place until everything around them has been documented. Pollen, charcoal, tiny flakes of flint, fish bones, plant seeds, all are collected together so that when a human bone does appear, you can see the entire micro-world it belongs to. The North Sea so far has given us far more random finds than proper sites. That's not because proper sites don't exist. It's because accessing them in a cold, turbid, busy shipping lane is hard. The few places where researchers have been able to work in a more controlled way, such as targeted investigations along pipeline routes or small area digs linked to wind farm projects, hint that when the conditions are right, whole occupation surfaces with hearths, post holes and scattered bones can survive intact. That's what makes those stray human bones caught in nets so tantalizing. They're not just morbid curiosities, they are signals. Each one is a flare fired up from a buried landscape saying there is a campsite here, or there is a burial ground not far from this coordinate. But it's not just fishing. Modern industry has become the biggest excavator of Doggerland. Whenever sand is dredged for beach nourishment or for construction, or when foundations are laid for offshore wind farms and pipelines, buckets and suction heads bite into the submerged landscape. They chew through buried riverbanks, old lake beds and former shorelines. Sometimes the operators notice something unusual in the spoil. A curved, dense object that isn't rock, a flint that's too sharp-edged and regular to be natural, a chunk of timber with tool marks. In the Netherlands and Belgium especially, where vast amounts of North Sea sand are pumped to shore, this has become a recognized phenomenon. People literally pick up pletoin animal bones and stone tools while walking on freshly replenished beaches. The sand they're kicking through was under 20 meters of water and several meters of overburden just months earlier. For big offshore wind projects, environmental regulations now often require some level of archaeological monitoring. That means that when drill rigs bring up cores or when dredging hits the right layers, at least some of the material is set aside and examined by specialists. From all of this activity, three broad categories of evidence have emerged as the headline clues that there was once a world here. Big mammal remains, human bones, and stone tools. The mammal remains are the most obvious and the easiest to find. Mammoth murs the size of bricks, woolly rhino horns, bison aurochs, horse, red deer, road deer, elk. Their teeth and heavy bones survive well and stand out in a net full of fish or a pile of dredged sand. Some are broken and rolled, battered by transport. Others are astonishingly fresh-looking with surface textures and even cut marks intact. They tell us that this wasn't an empty seabed. It was steppe, forest, wetland, crisscrossed by herds. Then there are the tools. Worked flints with sharp edges struck in distinctive ways. Mesolithic microliths, larger Paleolithic blades and cores, pieces shaped into scrapers and barren. Unlike bone, flint doesn't rot. A microlith sat in a Mesolithic campsite 9,000 years ago can be picked up today from a beam troll or a pile of dredged aggregate looking almost exactly as it did when it fell from someone's hand. When fishermen started bringing these in by the bucket full from certain areas, Dogger Bank, Brown Bank, other shallow shores, it became impossible to dismiss them as the occasional stray. There had been dense human activity out there. And then the most unsettling category, human remains, jawbones, teeth, bits of skull, long bone fragments, a brow ridge here, a child's mur there. They're rare, far rarer than animal bones, but they exist. Enough of them spread across enough years of finds that we can say with some confidence. People lived and died on what is now the seabed, and parts of their bodies still lie under the waves. But all of this bounty comes with a severe catch: context. The thing archaeologists value most is usually missing. On land, you might excavate a site sime by sime, mapping exactly where each artifact lay, what layer it came from, what it was next to. That spatial relationship, this charred nutshell next to that hearthstone under that post hole beside that burial, is the difference between we have a bunch of old stuff and we know what people were doing here on the North Sea floor. Most finds arrive in a fishhold or a sandy bee barge with their story already scrambled. A trawler might know roughly which rectangle of sea it was working that day, but not the exact spot where a particular bone entered the net. The gear itself drags and bounces. Objects are picked up, shifted along the bottom, dropped again. Some mix in the net before anyone sees them. Dredging processes are even rougher. Suction pipes and cutter heads can move material over hundreds of meters during extraction. Then pumps deposit sand in thick mixed layers elsewhere. By the time someone notices a mammoth tooth or a shard of human skull on a Dutch beach, it's already 2 or 3 times removed from its original resting place. And that original resting place mattered. Was that skull fragment eroding out of an old riverbank? Was it part of a burial near a lake shore? Was it lying in peat that formed in a reed marsh or in windblown sand on a dune? Without that context, we lose direct information about behavior. We have the who in the form of bones and tools and a very approximate where. But what exactly were they doing, and how was this place used to become much harder questions? So how do you salvage meaning from context-poor finds dragged up from a churned seabed? You start by squeezing every possible clue out of the objects themselves and by trying to reconnect them to the drowned landscape through other means. One fundamental technique is typology, sorting things into known kinds based on shape and manufacture. A particular style of microlith, a certain way of preparing a core, a distinctive antler harpoon form. These can be tied to rough time periods and cultural traditions because we've already dug them up in well-dated sites on land. If you find a trapezoidal microlith from the Brown Bank area that matches a style common in, say, 8th millennium BCE Denmark, you can tentatively slot it into that window. If a big carefully made leaf-shaped point turns up, you might think of late Paleolithic or very early Mesolithic hunters. Typology is not a magic time machine. Tool styles can linger or spread unevenly, but it at least stops everything from being an undifferentiated Stone Age blur. It lets us say this cluster of artifacts from this sandbank probably belongs to this slice of the past. Bones, whether animal or human, open up more options. Radiocarbon dating is the workhorse here. As long as there's enough collagen preserved in the bone, labs can measure the remaining radioactive carbon and estimate how long it's been since that organism died. When you apply this to a mammoth tooth from the seabed, you can tell whether you're looking at an animal that roamed a cold steppe 40,000 years ago or one of the very last mammoths in the region around 12,000 years ago. When you apply it to a human jaw, you can place that person within a specific millennial band of Doggerland's history. Radiocarbon has limits. Very old bones push the technique to its edge. Contamination can skew results, but over the last few decades, improved pretreatment methods have made it possible to date even poorly preserved underwater finds more reliably than before. Isotopes extend the picture further. The ratios of certain stable isotopes like carbon and nitrogen in bone collagen reflect diet. Marine foods, freshwater fish, terrestrial animals, and plants all leave slightly different isotopic fingerprints. So when you analyze a human bone from the North Sea, you can ask, did this person eat mostly land mammals? Were they heavily reliant on marine resources? That tells you not just about their menu, but about where they spent their time and how they organized their subsistence. Strontium and oxygen isotopes can, in some cases, hint at geographic origins and movement because they reflect the geology and water of the region where someone grew up. For Doggerland remains, that's still a developing field, but in principle, you can distinguish someone raised on chalky uplands from someone who spent childhood in a granitic or volcanic region. If we ever get enough well-preserved Dogon individuals, those isotopes might reveal whether people buried in one area were locals or came from further afield. Then there's sediment analysis, which is all about recreating the context that trolls and dredges have destroyed. Modern seabed mapping uses sonar to image the shape of the bottom and the layers beneath it. High-resolution bathymetry and sub-bottom profiling can reveal buried river channels, lake basins, peat layers, and erosional surfaces. If fishermen keep bringing up Mesolithic tools and red deer bones from a particular depth and area, geophysicists can go back and look at the acoustic data for that patch. Maybe it lines up with the edge of an old river terrace, or the shoreline of a paleo lake, or the margin of a peat bog. Suddenly, instead of somewhere in grid square X you'll find is probabilistically linked to a former riverbank here, active between these dates. Sediment cores are the ground truth for those interpretations. Scientists lower tubes into the seabed and extract columns of layered mud, sand, and peat. In those cores under microscopes, you can see pollen grains, tiny shells, bits of plant tissue, insect remains. Pollen spectra tell you what the surrounding vegetation looked like when that layer was deposited. Open steppe, birch scrub, pine forest, mixed hazel woods, datums and foraminifera. Microscopic aquatic organisms distinguish freshwater lakes from brackish estuaries or fully marine conditions. If a human bone or tool is found in sand that matches a particular horizon in a core, you effectively reattach that stray object to a known environment individually. Each technique gives only a sliver of information. Typology says late Mesolithic probably. Radioarbon says around 7,500 BCE, give or take a century. Isotopes say this person ate a lot of fish. Sediments say this was a river margin with alder and reeds, not a windswept dune. Together the slivers start to cohere. You can look at a jawbone hauled up in a trawl and say this was a person who lived about 8,000 years ago during a phase when Doggerland was already a wetland maze. They probably relied heavily on river and estuary resources. The bone most likely came from a cutbank along this relic channel, which at that time would have been a low bluff above a meandering river. That's not the same as walking into their camp and seeing them cook, talk, and sleep. But it's a long way from random bone from the bottom of the sea. There's one more ingredient that matters: repetition. One mammoth tooth is a curiosity. 10 mammoth teeth, a handful of bison bones, and multiple reindeer antlers from the same depth and region start to outline a faunal community for a particular time slice. One human femur is an oddity. A small scatter of human bones and Mesolithic tools consistently coming up from the flanks of a specific bank suggest a persistent place where people returned, hunted, fished, perhaps buried their dead. That's how from chaotic context poor finds patterns emerge. Certain shoals and banks become known as hotspots for particular kinds of material. Archaeologists collaborate with skippers who are willing to note positions, keep an eye out, and bring in unusual finds. Dredging companies partner on targeted surveys before they strip an area. Slowly, a loose mesh of evidence tightens, and as it tightens, the human bones become more than macabre curios in a display case. They become anchors, literal and figurative, tying an underwater sound map and a handful of flints and antlers to specific individuals. Which leads to the uncomfortable question at the heart of this story. Whose bones exactly are we hauling out of the North Sea? How did they end up there? And what, if anything, can their fragmentary remains really tell us about the people of this drowned land? That's where we turn next. When people hear human bones from the North Sea, it's easy to picture intact skeletons lying peacefully on the seabed, like bodies on a battlefield waiting to be discovered. That's not what we actually get. What turns up in nets and dredge piles are almost always pieces, isolated elements. A section of jaw with a couple of teeth. A bit of parietal bone from the side of a skull, a chunk of ferrous, the shaft broken at both ends. Sometimes a baby's tooth small enough to vanish if someone isn't paying close attention. And they don't all belong to the same world. Some of these bones really are ancient, Mesolithic, late Paleolithic, possibly even older. They come out of sediment that's been buried since Doggerland was dry land. The surfaces are worn but not destroyed. The color has shifted to that characteristic brownish or dark tone from long burial. Sometimes, if you're lucky, there's still enough organic material inside to test. Others are much younger, teeth that still look almost white, bones with surfaces that haven't had time to weather into that deep fossil patina. In a few cases, fragments have turned out to be medieval or even post-medieval shipwreck victims. People lost in coastal storms, sailors who never made it back to port. The North Sea has been taking lives for as long as people have been crossing it, and its shallows don't care whether someone lived 9,000 years ago or in 1900. So when a fisherman puts a human bone on the dock and asks, "Is this Doggerland?" the honest answer is maybe. It might be someone who lived in a hut beside a drowned river of that lost country. It might be a farmer from 3,000 years ago buried in a cliffside grave that later washed out. It might be a sailor from a ship sunk in the First World War. The mystery is to figure out which. To do that, scientists squeeze the same kinds of clues out of human bones that they do from animal remains and tools, then add a few more layers of detective work. The first pass is almost always morphology. What the bone looks like, what part of the body it is, and how it compares to known examples. An experienced osteologist can pick up a fragment and tell you whether it's human or animal, male or female, adult or child, the thickness of the skull, the shape of a tooth root, the curve and cross-section of a long bone shaft. These basic observations already narrow down the story. But to answer the question, Doggerland or not, you need time. That's where radiocarbon dating comes in again with a twist. If the bone still holds enough collagen, A lab can measure the surviving radioactive carbon and estimate when that person died. When researchers have done this on North Sea human remains, they've gotten a spread of ages. Some do cluster in the Mesolithic around the period when Doggerland was turning from a broad plain into a marshy archipelago. Others are clearly later: Bronze Age, Iron Age, Medieval. Even carbon isn't straightforward at sea. There's a complication known as the marine reservoir effect. Marine food webs recycle old carbon from deep water, which can make organisms that eat a lot of seafood look artificially ancient when you date their bones. If a Mesolithic hunter-fisher from Doggerland was eating mostly seals and fish, their collagen might carry a marine signature. If you run a standard radiocarbon date and ignore that, you'll think they died hundreds of years, maybe a millennium earlier than they really did. So for North Sea humans, labs don't just run a date and call it done. They look at stable isotopes in the same collagen, carbon and nitrogen again, to estimate how marine or terrestrial the person's diet was. Then they use correction models to adjust the radiocarbon age. It's not perfect and it adds error bars, but it's better than pretending everyone ate the same thing. Morphology and radiocarbon give you who and when. Sometimes there's just enough preserved DNA to ask where from in a deeper sense. Ancient DNA is fragile, and water is not kind to it. But cold oxygen-poor sediments can sometimes seal fragments off. A few North Sea human remains have yielded partial genetic profiles. Those results are still sparse and tentative, but they hint that at least some offshore individuals belong squarely in the same broad genetic pool as Mesolithic hunter-gatherers on adjacent coasts. Others from later periods line up with known European populations of their time. Put all that together, and you start to see the outlines of multiple stories mixed in one basin. That raises the next big question. How did those bodies or bits of them get from dry land into the middle of what is now a shallow, restless sea? One obvious pathway is the most direct. They didn't go anywhere. The sea came to them. Imagine someone buried on a low rise a kilometer inland from a Mesolithic shoreline. Their family dug a grave, maybe placed stones, maybe left offerings. For centuries, even millennia, that spot stayed dry. Then, as sea level crept up, the shoreline migrated landward. Waves began to undercut the bluff. Storm surges bit chunks out of it. At some point, the gravitop collapsed into the surf, scattering bones and grave goods. Tides and currents winnowed the material. Light objects and fine sediment washed away. Denser pieces like teeth and long bone fragments sank and rolled offshore. Eventually, they came to rest on the seafloor, perhaps to be buried again in new sand. The same thing can happen to any cemetery or burial ground positioned near a retreating coastline. Bronze Age burrows on low headlands, early medieval graveyards near eroding dunes. Over thousands of years, as the shoreline steps inland in fits and starts, those once peaceful resting places get fed into the coastal erosion machine and spat out into the shallow marine zone. Rivers are another pathway. All the great rivers draining into the North Sea, the Thames, the Rhine, the Meuse, the Schell, the ELB, have been moving sediment and occasionally people towards the basin for as long as they have existed. When those rivers cut into old terraces or flood through burial sites on their banks, they can entrain bones along with gravel and wood. A femur eroded out of a Roman riverside grave in Germany could spend decades or centuries tumbling downstream, snagged, rearied, freed again, until it finally reaches the estuary and is swept onto the continental shelf. Then there's Doggerland itself. Before the sea flooded it, the plain had its own rivers, lakes, marshes, and banks. Mesolithic people would have buried their dead in certain spots, higher ground, sheltered bluffs, maybe near important campsites or ritual locations. As sea level rose and channels widened into estuaries, those internal banks became coastal cliffs. Graves eroded just like any other, their contents following the same pattern of collapse, scattering and rearing. Not all offshore human remains, though, need a slow geological explanation. Some are almost certainly tied to very recent, very human catastrophes. The North Sea is notorious for shipwrecks. Medieval cogs, Dutch East India men, warships from every era, fishing boats, cargo steamers, submarines, passenger ferries, thousands of wrecks dot the seabed. When a wooden hull goes down in a storm or under enemy fire, it doesn't sink neatly to the bottom and stay there unchanged. Waves tear at superstructures. Sediment moves. Later trolling can rip open buried wrecks. Bones initially trapped inside can be freed and scattered, ending up far enough from the original site that someone finding them in a net wouldn't immediately associate them with a known wreck. Even without wrecks, the historic and modern North Sea has claimed people off open decks, from lifeboats, from aircraft. Not every body was recovered. Over decades, skeletons on or in the seabed can come apart, each piece going its own way in the currents. Some of the mystery bones that occasionally surface are soberingly, probably from losses within the last few centuries. Occasionally, forensic examination makes that obvious. A bullet embedded in bone of a modern caliber, or cut marks from steel tools, or pathology consistent with industrial age disease. Archaeologists and physical anthropologists have to juggle all these possibilities when a new find comes in. They can't just assume Stone Age. Every piece of evidence, morphology, wear, color, radiocarbon, isotopes, possible DNA has to be weighed against multiple scenarios. Doggerland burial, later prehistoric grave, historic cemetery erosion, shipwreck, modern loss. Behind that scientific puzzle lies an uncomfortable fact. These are people, not just data points from a vanished landscape. Not just evidence for a cool, lost country story, but individuals who once had families, languages, fears, and hopes. Treating their remains as curiosities or trophies sits uneasy with modern ethics. On land, most countries now have clear rules about how to handle human remains. There are time thresholds. Older than a certain number of years, they're considered archaeological, younger, and they fall under forensic or religious law. There are procedures for excavation, analysis, reburial, and consultation with descendant communities. Offshore, in a mixed environment like the North Sea, those neat categories blur. A jawbone hauled up by a Dutch beam TWLR might be Mesolithic, or it might be from a World War II sailor. It might demand careful lab work and then respectful reinterment as an archaeological find. Or it might trigger a forensic investigation if there's any chance it's recent. Different countries bordering the North Sea have developed their own protocols, but a few principles are widely shared. Finds that look recent or that could plausibly be linked to identifiable individuals are reported to authorities, sometimes even to war graves. Bones that are clearly ancient, once documented and sampled, are usually curated in museum collections, stored under conditions that slow further degradation, available for future study when better methods appear. Even then, there's debate. How much sampling is justified? Every radiocarbon date and DNA extraction consumes part of a finite object. Is it right to drill into someone's tooth enamel to run an isotope study that may or may not yield clear results? At what point does the scientific value outweigh the instinct to leave the dead undisturbed? For some, the answer lies in what we can give back in return. By studying these offshore remains, we're not just satisfying curiosity. We're reinscribing people into the story from which rising seas literally erased them. Without names, without faces, but with as much dignity as we can manage, we're saying, you were here. You lived in this place. Your existence mattered enough that thousands of years later, strangers are trying to piece your world back together. That doesn't dissolve the ethical tension, but it frames it. Every time a North Sea bone is lifted from a net and passed carefully into a paper bag instead of the bin, someone has decided that this individual, whether they died 10,000 years ago on a river bluff or 100 years ago in a steel hull, deserves more than to be thrown away. In that sense, the human bone's mystery is double. On one level, it's about technical questions: age, origin, pathway to the seabed. On another, it's about how we, the inheritors of this changed coastline, choose to relate to the dead whose physical traces still drift up out of it. Are they specimens, ancestors, casualties, all of the above? And while we wrestle with that, the sea keeps doing what it's always done, eroding, shifting, uncovering. Every storm cuts a little deeper into submerged banks. Every year, fresh material is turned over, and a few more bones, human and animal, edge closer to the surface where a net or a dredge can reach them. Which brings us to the slow, implacable force behind this entire story. Those bones are out there scattered across the seabed because the land they belong to didn't vanish in an instant. It drowned gradually, fitfully over thousands of years in a way that people living on it would have seen and felt within a single lifetime. To understand Doggerland and some of the human remains we now find offshore, we have to understand that long, relentless rise of the waters. At the end of the Ice Age, nobody woke up to find the North Sea roaring over the horizon in a single apocalyptic wall of water. The real killer was quieter and far more patient. It started far away on ice sheets nobody in Doggerland would ever see. As the last glacial maximum eased, enormous domes of ice over North America and Northern Europe began to melt. Not in a day, not in a decade, but continuously, season after season. Every summer, more meltwater poured into rivers, lakes, and ultimately the oceans. Global sea levels rose on average a few millimeters. That doesn't sound like much. On human timescales, a few millimeter is invisible. But stack that up over a century. You're talking tens of centimeters, over a millennium meters. Over the roughly 10,000 years after the peak of the last ice age, sea level climbed by something like 120 meters worldwide. Viewed from orbit, it was a simple physical process, a planetary bathtub filling up. Add water, all the oceans rise together. But coastlines are where that abstract curve turns into real consequences. And coastlines don't behave like tidy lines on maps. When people talk about Doggerland going under, it's tempting to picture a flat floor and a steady, even rise like water creeping up stage scenery in a slow-motion disaster movie. In reality, the North Sea basin was a complex three-dimensional landscape. Low river valleys, peat-forming basins, high revel ridges, dunes, cliffs, channels that cut deep then silted up. As global sea level rose, that complexity meant the water didn't simply advance like a calm, even tide. It surged into some places early and bypassed others, paused behind natural barriers, then punched through in sudden shifts. Coastal geomorphologists sometimes call it bathtub plus weather. The bathtub part is the global component, the steady climate-driven increase in average sea level. The weather part is everything that actually moves the shoreline. Storms, waves, tides, currents, sediment supply, local subsidence or uplift. Those are noisy, spiky processes laid on top of the smooth rise. For people living on the plain, the long-term trend would have been almost impossible to ignore. But not because they had tape measures on the beach. They would have felt it in memory. Picture a community living on a low but solid rise a few kilometers back from an esty. When the oldest person in the camp was a child, they might have walked through a band of open woodland to reach the shore. Maybe there was a particular oak that marked the path, a place where shellfish were reliable, a sandbar that emerged at low tide. By the time that person's grandchildren were born, that oak was standing in wet ground most of the year. The path turned to muck after rains. The sandbar barely cleared the waves on the highest tides. Winters began to bring more frequent, more destructive storm surges when wind-piled water pushed far inland. On those nights, the sea would seem to leap forward, pouring into hollows that had been dry for generations. In the first phase, the change would have looked like encroaching marsh. Freshwater wetlands expand as the water table rises and drainage backs up. Pools linger longer after floods. Channels splay into multiple braids. Solid paths turn into spongy ground. For a while, that could even be good news. More reeds, more waterfowl, more fish in the new backwaters. Mesolithic people were experts at exploiting ecotones, the edges between land and water. A growing marsh is a growing edge. But as the global sea level kept climbing, the nature of that water began to shift. Salt water pushes inland along estuaries and under coastal aquifers, a process known as saltwater intrusion. In the North Sea basin, rising seas would have transformed lower river reaches from purely freshwater systems into tidal estuaries, then into broad brackish inlets. Floods that had once brought silt and life-giving nutrients now pushed salty water over low fields and through the roots of trees that were never meant to taste the sea. Over generations, familiar stretches of forest along low valleys would thin and retreat upslope. Alder and willow might hold on a bit longer in the wet, but oak and pine on the lower flats would sicken and die as their roots periodically sat in brackish water. Trunks that once anchored dry trails became gray, drowned snags, standing waist-deep in tidal channels. Deadwood attracted different animals, different insects, different birds. The songs at dawn would change even before the skyline did. Higher ground, meanwhile, would become more precious. As the lower reaches turned to swamp, communities would shift their campsites upslope to ridges and islands that stayed reliably dry. Places that had once been peripheral suddenly became central. A modest hill overlooking a river bend might turn into a seasonally crowded hub, filled not just with one band but with visitors from other groups, using it as a staging point to cross the widening water. And the water was widening. That's another way people would have felt the drowning in their legs and their travel routes. For hunter-gatherers, movement is survival. Trails, crossings, fords, and habitual circuits between resource zones are as essential as any house or tool. Sea level rise slowly eats those circuits. The shallow channels that once could be waded at low tide became too deep, the currents too strong. A foring spot where grandparents once walked with baskets held high might become a swim, then a no-go. Paths that skirted the margins of old lakes disappeared under red beds. Over decades, what had been a continuous overland route from one hunting ground to another fragmented into a series of water crossings. People adapted because they always do. Boat technology in the Mesolithic wasn't an optional luxury in places like Doggerland. It was the connective tissue of daily life. As the water networks grew and the land fractured into peninsulas and islands, dugout canoes and simple rafts became more central. Children who once learned the landmarks of overland trails now learned currents, eddies, and the habits of the tides. But each adaptation came with trade-offs. A crossing that's only possible by boat is more vulnerable to storms and accidents than a trail on dry land. A safe landing beach can be wiped out by one winter's erosion, replaced by a steep wave-cut edge where boats can't easily be pulled up. And every storm has the potential to redraw the map overnight. Storms are the spikes on that smooth sea level curve. For years, the shoreline might seem stable. Creeping marsh here, a bit of bank erosion there. Then a big surge hits. One winter, a particularly violent North Sea storm drives water far inland. Waves chew at a low bluff that has been gradually undermined for decades. Overnight, meters of land collapse. A little grove of trees where people stored gear or cached food is simply gone. Its root mat hanging over a fresh scarp. A burial on that bluff placed there generations before when the coast was distant suddenly lies in a vertical face of mud and peat. The next tide pulls the grave apart. From the perspective of global sea level graphs, nothing special has happened. The long-term rate hasn't changed. On the ground, a single night has erased a place that anchored stories, memories, and roots. Now scale that up to centuries. The North Sea basin didn't have just one storm like that. It had thousands. Each one nibbled away at some stretch of coast, opened a new channel, breached a barrier bar that had been holding back the sea from an inland basin. Once a barrier is gone, the water spreads quickly into the lands behind it, flooding what had been a patchwork of freshwater lakes and bogs and turning them into tidal lagoons. Ecologically, that meant constant rearrangement. Wetlands are dynamic even without sea level rise, but under a rising sea they become laboratories of change. Freshwater reeds give way to salt-tolerant grasses. Shellfish communities shift from freshwater mussels and snails to cockles and oysters. Fish species change. Birds that prefer mudflats and tidal shallows move in where forest ducks and marsh heron once dominated. For Neolithic people, this wasn't just background scenery. It altered the economics of survival. Old reliable spots, a salmon run at a narrow point, a beaver pond, a berry-rich brush patch might fail. As the hydrology changed, new opportunities opened elsewhere. Rich shell mittens on tidal flats, seal hallouts on newly exposed sandbars, waterfowl concentrations in brackish lagoons. People who could track and exploit those shifts had an edge. Groups responded in different ways, and not all at once. Some likely practiced a form of retreat and renewal, abandoning low camps as they flooded, moving inland or to higher ridges. Then building new seasonal patterns around the changed shoreline. Oral traditions may have encoded knowledge about which places the water took and which remained safe. Elders could point to drowned tree stumps and tell younger people, "We used to live there," turning visible loss into practical warning. Others may have leaned into the water worlds emerging around them. Archaeological finds from the fringes of what used to be Doggerland suggest intensifying use of aquatic resources in the late Mesolithic. More fish bones, more seal and waterfowl, more tools associated with nets and traps. Rising seas didn't simply push people away. They also pulled some lifestyles toward the coasts. At the same time, long-distance connections had to flex. Routes that once ran straight across the plain were broken by expanding inlets. To reach trading partners or kin groups, people now had to detour around flooded basins or develop reliable boat crossings. A journey that a grandparent had made in 2 days on foot might, in the grandchildren's time, require a boat segment and careful timing with tides. The geography of social life stretched and twisted. Some contacts would have been severed altogether as arms of the sea deepened and widened into real barriers. An ally on what slowly turned into an island might become harder and harder to visit until seasonal gatherings dwindled and then stopped. From their perspective, the mainland was slipping away just as surely as they were. There's another layer to this human response that rarely gets discussed: emotional climate. Living through slow drowning means inhabiting a landscape that is constantly reminding you of impermanence. Children grow up with stories about places out there that no longer exist above water. Landmarks vanish within a human lifespan. Graves are not as permanent as people once thought. Even if nobody ever framed it as sea level rise, the pattern would have been hard to miss. The water always wins given time. That doesn't mean people sat passively watching their world disappear. They moved, they innovated, they reconfigured their territories and alliances. But they were doing all that under a moving ceiling. Every adaptation bought time, not final security. Eventually, for Doggerland, that ceiling came down. What had been a broad habitable plain was reduced to a network of low islands and peninsulas, refugees of higher ground in a matrix of tidal shallows. The ecological richness probably remained high, maybe even peaked in some ways. Fish, birds, marine mammals, shellfish, freshwater, and saltwater, all jostled together. For a while it may have been an extraordinarily productive, if precarious place to live, and then the margin narrowed too far. Camps that had once been central turned into seasonally flooded spots. The last high ridges became isolated islets. A single storm could temporarily wash over them. At some point it stopped making sense to stay. The people whose descendants now live around the North Sea's edges shifted their weight fully onto the surviving coasts of Britain, Scandinavia, the Low Countries, and beyond. What they left behind wasn't a clean, empty seabed. It was a palimpsest of drowned forests, silted channels, eroded graveyards, and scattered tools and bones, all of it slowly being worked over by waves and currents. When we find a human femur in a troll net today, we're touching the long tail of that process. That bone didn't leap from a hillside into the deep. It rode this slow drowning step by step as sea level climbed and storms did the rest. But alongside this drawn-out catastrophe, there were also punctuations, events that weren't just another bad winter that hit hard and fast. If the background story of Doggerland is millimeters per year, one of its most dramatic chapters was written in hours. That's where the Storegga Tsunami comes in, and why some researchers think that for at least part of the plains population, the end might have felt anything but slow. Around 8,000 years ago, something happened far to the north that had nothing on the face of it to do with the people living on the last scraps of Doggerland. It started off Norway on the edge of the continental shelf in a place we now call the Storegga Slide. For hundreds of kilometers, the seabed there had been loaded with loose water-rich sediments. Glacial mud dumped off the front of ice sheets, then stacked and over-steepened by currents and more sediment on top. Think of a colossal underwater slope made of half-set pudding held in place by friction and luck. At some point, that luck failed. Whether triggered by a small earthquake, gas hydrate destabilization, or just the slow build-up of stress, an enormous swath of the seabed detached and slumped downslope. Not a neat single block, but a cascading failure. Sediment packages collapsing, accelerating, plowing into deeper water and fluidizing as they went. In a matter of minutes to hours, somewhere on the order of 3,000 cubic kilometers of material, enough to cover a country in mud hundreds of meters thick, moved underwater, but violently. When that much seafloor shifts, it doesn't just sit there quietly. It displaces water, a lot of water. That displacement is what generated the wave, a tsunami sweeping outward from the Norwegian margin, spreading across the North Atlantic and into the then shallower North Sea basin. In deep water, tsunami waves are long and low, more like a rapidly moving hump than a breaking crest. They can travel hundreds of kilometers at jetliner speeds while barely ruffling the surface from a ship's perspective. It's when they approach shallower shelves and coasts that they pile up, slow down, and become walls of water. The Storegga event is one of the best documented prehistoric submarine landslides we know of. Its scars are still visible on modern biometric maps of Norway. Huge scalloped headwalls, slide blocks, and debris fields. Offshore cores capture the chaotic deposits of the slide itself. That part of the story is on pretty firm ground. A massive submarine landslide happened, and it was big enough to create a tsunami disturbance. The harder question is what that meant for Doggerland. Over the past few decades, researchers have been hunting for tsunami fingerprints around the North Sea. Thin, distinctive sand layers laid down over pets and soils that were once at or just above sea level. In eastern Scotland along the Moray Firth and in low-lying estuaries they found them sheets of marine sand draped across old marsh surfaces, sometimes containing marine microacyls and ripped-up peat CLS, sometimes interbedded with Tiddly-influenced muds. Radiocarbon dates on the pets and organic layers bracket those deposits to around 8,200 to 8,100 years ago, squarely within the window for the Storegga Slide. Similar deposits have been identified on parts of the Shetlands and the Orkneys. And hints of related layers appear in coastal sequences further south, northeastern England, parts of Denmark, even around the southern North Sea margins. The exact correlation isn't always airtight. Dating uncertainties, local reworking, and later erosion all blur the picture, but taken together, they look very much like the landward splash marks of a large wave striking multiple shorelines around the same time. To cross-check the geology, scientists have turned to numerical models. Feed in a reconstruction of the Storegga Slide volume and geometry. Add bathymetry for the early Holocene North Sea, shallower than today with more banks and islands and fewer deep channels. Let the physics run. What you get are wave fields that radiate out and refract through the basin, focusing energy in some corridors, dissipating it in others. Those models suggest that parts of the Scottish and Norwegian coasts could have seen run-up heights of 10 to 20 meters above local sea level. In more sheltered, distant areas, modeled wave heights are lower, a few meters, maybe less depending on the details of the paleogeography. For the Doggerland region, the low-lying plains and shores that are now the central North Sea, the simulations are trickier. Much depends on exactly how much of the plain was already underwater, how continuous the channels were, and what sort of banks or islands stood in the wave's path. This is where the debate begins. One interpretation popular in documentaries and headlines imagines Storegga as the final blow. In this version, Doggerland is already reduced to a patchwork of marshy islands and low spits by millennia of rising seas. People cling to the last habitable high spots. Then one day, the sea doesn't just creep forward, it charges. A wall of water races across the shallows, overtops the last refugees, and scour away settlements and soils. From that point on, the story says Doggerland is effectively gone as a place to live. It's a powerful image. It gives a satisfying narrative punctuation mark to an otherwise slow, ambiguous drowning. It also might be too neat. An alternative view sees Storegga not as a singular apocalypse, but as one very bad day, possibly several bad days within a much longer process of loss. In this version, the tsunami hits a Doggerland that is already severely fragmented. Much of the central plain is subdued by shallow tidal water. The remaining land is a chain of low islands and peninsulas at different elevations with wetlands and lagoons in between. Some of those islands are high enough or sheltered enough that even a several-meter wave does not raise them entirely. Others are less lucky. That variation, who got lucky and who didn't, comes down, as tsunamis always do, to topography. Tsunami impacts are profoundly local. A coastline that looks broadly low-lying on a regional map can at ground level contain all sorts of microtopographic defenses and vulnerabilities. A gently shelving beach facing directly into the oncoming wave acts like a ramp, letting the water climb far inland. A steep bluff with deep water just offshore may take the brunt as crashing energy at the base of the cliff with less inland flooding. An embayment shaped like a funnel or a V can focus and amplify the wave, whereas a bay that opens away from the wave's main direction may be partly shadowed. Now translate that complexity into the semi-drowned world of Lake Doggerland. You have sinuous tidal channels occupying former river valleys flanked by peat-forming flats. You have sandy barrier bars separating shallow lagoons from the open sea. You have residual gravel ridges, old river terraces or glacial marines sticking up just high enough to stay mostly dry above spring tides. You have relic dunes that form narrow, elevated spines. When a tsunami sweeps through that kind of landscape, it doesn't just roll in as one uniform front. Wave energy threads down the deepest channels, surges into inlets, wraps around headlands, and diffracts behind higher islands. Behind some natural barriers, wave height decays quickly. Behind others, it stacks up as water is forced into narrowing spaces. A camp on a low terrace that faces into a broad estuary might be obliterated, while a camp a few kilometers away, tucked behind a sand ridge and oriented away from the main approach, might be flooded, battered, but not entirely erased. This is not speculation in the abstract. Modern tsunamis like the 2004 Indian Ocean event or the 2011 Tohoku tsunami in Japan show exactly this kind of patchiness. Two villages separated by a headland can experience radically different levels of destruction. One is flattened, the other damaged but largely standing. The difference is often tens of meters of relief or the presence of a natural or artificial barrier. For Doggerland, we don't have before and after photographs. We have at best a handful of cores and seismic lines suggesting where peat once accumulated and where marine sands later swept in. In some cores from the southern North Sea, researchers have identified sand layers overlying pits that might represent tsunami incursions, thin sheets of marine sediment draped over former terrestrial surfaces. But correlation to Storegga specifically is hard. Radiocarbon dates can be imprecise. Later storms can rework older deposits. Local subsidence or compaction can distort the stratigraphy. So the argument about Storegga's role comes down to lines of probability. On one side, the demonstrated existence of a very large submarine landslide, clear tsunami deposits in multiple parts of the region, numerical models showing energy reaching the central North Sea, and the fact that much of Doggerland by that time was low, close to sea level, and thus vulnerable to extreme flooding. On the other side, the already advanced state of Doggerland's fragmentation by 200 years ago, uncertainties in exactly how the wave would have interacted with that intricate landscape, and the recognition that even a devastating tsunami is temporary, a spike on a long-term curve dominated by gradual sea level rise and repeated smaller storms. If you lived there, the distinction between final blow and severe episode in a long decline would have been less academic and more geographical. For some communities, especially those on marginal low islands or close to the exposed northern fringes, Storegga might have been cutting. Camps washed away, boats destroyed, people drowned, soils stripped or salted, familiar paths erased overnight. For others in more sheltered pockets it might have been terrifying but survivable, water pouring across known ground. Yes, but receding, leaving a damaged but recognizable world. Those surviving pockets could become crucial in the aftermath. A tsunami doesn't just bring water, it moves sediment and debris. It can rake the surface clean in some places, bury it under fresh sand in others. In rice-growing deltas today, communities sometimes recover within a few seasons if the salt flush is brief and sediment deposition modest. In thin pay soils like Dogans, heavy saltwater intrusion could ruin certain plant communities for longer, forcing shifts in diet and settlement. But it doesn't magically erase higher, better drained ridges from the map. In other words, there is room in the physical reality for Storegga to have been both a lethal catastrophe in some sectors and yet not the moment when the last human footstep left the Dogger Bank. The frustrating part is how much we still don't know. We don't yet have a high-resolution times-list map of Lake Doggerland's surface at the scale that really matters for tsunami modeling. A map with meter-scale detail of ridges, channels and basins as they existed around 200 years ago. Most reconstructions are smoothed, based on modern bathymetry back projected with broad sea level curves. That's like trying to predict flood damage in a city using only a regional topographic map without the street grid. We also lack a dense network of well-dated cores across the former plain that could capture any tsunami sand sheets directly. The North Sea is huge and costs are expensive. A few key sequences tell us that there were sudden marine incursions. They don't yet let us trace those sheets as continuous carpets that can be tied unambiguously to Storegga's wave. Future data could change that picture dramatically. More detailed seismic surveys over the central North Sea could refine our reconstructions of ancient river systems, banks and islands. Focusing campaigns aimed at suspected shoreline positions identified from those seismic lines might capture the telltale structure of tsunami deposits. Sharp basal contacts, graded sands tapering inland, specific suites of microfossils. Improved dating techniques and Bayesian modeling could squeeze the age ranges tight enough to distinguish Storegga from other high-energy events. On the modeling side, feeding those refined paleogeographies into new tsunami simulations would let researchers test different scenarios. How high would the wave run if this channel were 10 meters deeper? What if this barrier bar had already been breached by normal storms? Which refuges remain dry under a 3-meter wave versus a 6-meter one? Those experiments won't give us a single definitive picture. But they can bracket the possibilities and help us understand what kinds of impacts are physically plausible. Even then, some things will remain unknowable. We will never be able to say whether a particular femur lifted from a troll net today belonged to someone who died in the Storegga tsunami, or someone whose grave eroded in a storm 3 centuries earlier, or someone who simply lived and died on a ridge that was later undermined by ordinary coastal erosion. The sea is not generous with that level of narrative detail. What we can say cautiously is that by the time St. Gas wave rolled through, Doggerland was already in its final act. Relentless sea level rise had done most of the structural work, turning a once continuous country into a scattering of low islands. The tsunami added violence to that slow suffocation, ripping, salting, and shocking the system in ways that must have been unforgettable for those who survived it. But it didn't create the drowning out of nothing. It rode atop it. In some ways, that makes the story more unsettling. There was no single moment when the entire country vanished in one cinematic surge. There were centuries of narrowing options interrupted by disasters that made the narrowing suddenly brutally obvious. Storegga was probably one of those. A spike of hours in a process measured in millennia. Somewhere in the middle of the North Sea, a trawler is hauling up its nets. The crew works as fishing crews have for generations, sorting through the catch, returning what they don't need, keeping what they came for. But then something comes up that isn't a fish. It's long, dense, gently organic in a way that catches the light differently. One of the crew picks it up, turns it over in their hands. It's a bone, a human bone. And it isn't the first time this has happened. It won't be the last. This isn't a horror story, though it sounds like one. And it isn't a mystery in the crime sense, though the questions it raises are just as gripping. What it is a window. A window into a world so ancient and so completely gone that most people have no idea it ever existed. A world that didn't sink overnight. A world that once stretched for hundreds of miles, where there is now nothing but open water, grey waves, and the occasional unlucky trawler pulling up something that has no business being at the bottom of the sea. The place has a name, Doggerland. And if you've never heard of it, that's about to change. 'Cause the story of what lies beneath the North Sea is one of the most extraordinary lost chapters in human history. Here's what makes this so genuinely strange. The North Sea today is busy, industrial, thoroughly mapped. Oil rigs, shipping lanes, wind farms. We treat it like empty space that has always been there. But between roughly 18,000 and 6,000 years ago, much of what is now the southern North Sea was dry land. Not shallow coastline, not a marsh, but actual inhabited landscape. Hills, rivers, forests, wetlands, animals moving through it, people living on it, hunting, fishing, raising families, burying their dead. An entire functioning world that modern Europe has completely forgotten. Not because the records were lost, but because the records are sitting under 30 to 40 meters of cold theater. And every so often, those records come up in a net. Now, here's the thing that should make you pause. When fishermen haul up a bone, there's a genuine and complicated question about what it can actually tell us. Human remains that have spent thousands of years on a seabed go through extraordinary chemical and physical changes. They get moved by currents. They get tumbled around by trolling. The context that an archaeologist would normally rely on. Where the bone was found in relation to everything around it, what layer of sediment it came from, what other objects were nearby. That context is often completely destroyed by the time it reaches the surface. So, the bones are both precious and frustratingly incomplete. They tell us people were here. They can sometimes tell us when through radiocarbon dating. They struggle to tell us much else, but the bones aren't alone. Fishermen have also pulled up antlers, worked flints, ancient tree stumps, mammoth teeth, even what appear to be tools shaped by human hands. All of it coming up from a seabed that was not so long ago in geological terms a landscape, where you could have walked from Britain to the Netherlands without getting your feet wet. That idea that Britain was simply not an island for most of the time modern humans have existed in Europe is the kind of fact that takes a moment to fully land. Read it again if you need to. Britain not an island, connected by land to continental Europe. And the place where that connection existed is now one of the busiest stretches of open water on the planet. So what happened? How does an entire landscape disappear? How do people who lived on it vanish from the historical record so completely that we're only now beginning to piece their story back together? And why, after thousands of years underwater, are their bones still drifting up to the surface? Those are the questions this journey is going to answer. We're going to go deep into the geology of how Doggerland formed, how it changed, and how it ultimately drowned. We're going to look at what archaeologists have managed to learn about the people who live there, their tools, their shelters, their beliefs, and their daily lives. We're going to explore the dramatic events that may have accelerated the flooding, including one catastrophic moment that would have been almost incomprehensible to anyone alive to witness it. And we're going to look at the cutting-edge science being used right now to map a world we can no longer visit on foot. Because here's what keeps scientists genuinely obsessed with this. Doggerland isn't just a curiosity. It isn't just a flooded field. It was at various points in its existence some of the most productive and livable land in prehistoric Europe. The people who lived there weren't primitive. They were skilled, adaptable, successful hunters and gatherers who had figured out how to thrive in a landscape that no longer exists. Understanding their world could fundamentally change how we think about the peopling of Europe, the development of early cultures, and the way human societies respond to catastrophic environmental change. That last part feels uncomfortably relevant. Before we go any further, though, I want to know where you're listening from right now. Drop it in the comments. What time is it there? And where in the world are you? I check these and I genuinely love the range. Someone in Melbourne at 2 a.m., someone in Chicago over their morning coffee, someone in Oslo on a lunch break. There's something fitting about that. People scattered across the globe, connected by curiosity about a world that was itself lost to rising water. So if you're here, say hello. Tell me your location and your local time. And then let's go back before the sea. Back when the land we now call Britain wasn't an island at all and the North Sea was a river valley. To really understand what's sitting under the North Sea, you need to do something that goes against every instinct you have when you look at a map. You need to drain it. Not in your imagination all at once, like pulling a plug, but slowly the way it actually happened in reverse. Because the world we're talking about didn't just appear one day. It was built over tens of thousands of years by forces so large that individual human lifetimes were completely irrelevant to them. We're going back to the last glacial maximum roughly 20,000 years ago. And the first thing you need to know is that the planet looked almost nothing like it does today. Ice sheets that we can barely conceive of, some of them 2 or 3 kilometers thick, were sitting on top of what is now Scandinavia, Scotland, much of northern Britain and large portions of northern Europe. The sheer weight of that ice was compressing the land beneath it. But more importantly for our story, that ice represented an almost incomprehensible volume of water that was no longer in the ocean. It was locked up on land. And when water leaves the ocean and sits on continents as ice, sea levels drop. Globally, during the glacial maximum, sea levels were somewhere around 120 meters lower than they are today. Think about what that means. 120 meters. That's not a slightly different coastline. That's an entirely different planet. Where the southern North Sea now sits, the seabed was dry land. Not flooded land, not recently drowned land, just land. Rolling, complex, geologically real land with rivers cutting through it. Sediments building up over millennia. Ecosystems establishing themselves and evolving. The river, which today flows through Germany and the Netherlands before emptying into the North Sea, didn't stop at the Dutch coast back then. It kept going, collecting the temperatures, collecting other rivers we no longer have names for, draining a vast continental plain before eventually reaching the Atlantic somewhere far to the northwest of where the ocean sits today. Britain wasn't an island because it didn't need to be. It was just the western edge of a much larger landmass. And that landmass, that particular stretch of it between what is now eastern England and what is now Denmark, is what we call Doggerland. Now, the name Doggerland needs a small unpacking because when people first hear a country beneath the sea, the word country can mislead them. We're not talking about a nation. We're not talking about borders, flags, governments, or any of the things the modern mind attaches to the idea of a country. What we're talking about is a landscape, a territory. A region of the Earth's surface that was for a very long time inhabited by people who had as much claim to it as anyone has ever had to anywhere. It was their home in the most fundamental sense. They were born there. They died there. And as far as we can tell, they had no particular reason to think it would ever be anything other than what it was. This distinction matters because Doggerland's significance to European prehistory isn't political. It's ecological and demographic. At its greatest extent, this was potentially some of the richest land in Ice Age and post-Ice Age Europe. Wetlands, estuaries, river valleys, open grassland, coastal resources. The kind of landscape that would have been extraordinarily productive for hunter-gatherer societies. Not marginal, not difficult, but genuinely abundant. Understanding who lived there and how they lived there could rewrite significant chunks of what we think we know about the early human settlement of northwestern Europe. Now, within Doggerland, there's one feature you'll hear mentioned more than any other. The Dogger Bank. This is a large, shallow sandbank that sits in the central North Sea. And today it's famous mostly as a fishing ground, one of the richest in the world. Fishermen have worked it for centuries. But the reason it's so relevant to this story is that during the height of Doggerland's existence, the Dogger Bank would have been a significant elevated area, a high point on the landscape, hills, probably maybe quite substantial ones, As sea levels began to rise and the surrounding lands started to flood, the Dogger Bangkok region would have remained dry for a long time, becoming first a peninsula, then an island, then a shallow sandbank, and finally disappearing beneath the waves entirely. If you're looking for the last holdout of Doggerland, the final piece of land that went under, the Dogger Bank is your best candidate. Which makes the things fishermen pull up from that particular patch of seabed especially interesting. So, let's establish the timeline because it matters for everything that comes after. Around 20,000 years ago, glacial maximum, ice everywhere, sea levels at their lowest, Doggerland at or near its greatest extent, though it would have been cold, periglacial, not necessarily the most hospitable place in the world. Think tundra more than forest. Then the ice starts to melt. This isn't a sudden event. It's a process that takes thousands of years with warmer periods and temporary reversals and sudden collapses, but the general direction is clear. Ice melts, water returns to the ocean, sea levels rise. Between about 18,000 and 8,000 years ago, sea levels globally rose by something in the range of 100 meters. That is an extraordinary amount of water returning to the world's oceans in what is geologically speaking an eye blink. For Doggerland, this means the window of habitability as a rich, temperate, productive landscape falls roughly between about 12,000 and 6,000 years ago. After the worst of the ice had retreated, after the climate had warmed enough to support forests and rich ecosystems, but before the sea had risen enough to claim the land entirely. The people we're most interested in, the Mesolithic hunter-gatherers who would have known Doggerland at its peak, were living in that window. A world that was by many measures extraordinarily good to live in, and that was simultaneously and visibly slowly being taken from them. By somewhere around 6,500 years ago, give or take, the southern North Sea as we know it was largely in place. Britain was an island. The connection was gone, and the people who had lived on that land, their camps, their paths, their hearths, their graves were underwater. The timeline you want to hold in your mind going forward runs from the glacial maximum through the warming period, through the flourishing of Doggerland as inhabited landscape, through the slow and then accelerating inundation to the final disappearance of the last islands around the mid-Holocene. That's roughly a window of 14,000 years, longer than all of recorded human history, long enough for entire cultures to rise and fall and be forgotten on land that no longer exists. And here's the thing that should keep nagging at you as we go deeper into this story. The people who lived in that window didn't experience it as a slow catastrophe. They experienced it as their lives, season by season, generation by generation. The change was real, but it was happening at a pace that made it almost invisible to any individual human being, which raises a question that archaeologists are genuinely wrestling with. Did they know what was happening to them? And how did they respond when the water finally made it impossible to ignore? That's where this gets truly extraordinary. But before we get there, we need to understand what Doggerland actually looked like. Not as a blank space on a draining map, but as a real complex living landscape. So what did it actually look like? Not in the abstract, not as a theoretical patch of exposed seabed, but as a physical place with texture and variation and geography that would have shaped everything about how people moved through it and where they chose to live. The answer starts with ice. Not the ice that was sitting on top of Doggerland, but the ice that was sitting north of it, because glaciers don't just sit there. They move, they grind. They push enormous quantities of rock and sediment ahead of them like slow bulldozers, operating on geological timescales. And when they retreat, they leave behind a landscape that's been fundamentally restructured, valleys carved deeper than they would otherwise be, basins scooped out of bedrock. Vast quantities of sediment deposited in patterns that reflect the direction and speed and temperature of ice that has since completely vanished. The topography of Doggerland wasn't random. It was sculpted, and understanding the sculptor helps you read the landscape it left behind. During the most intense glacial periods, ice sheets extended over much of what is now the northern North Sea. As those ice sheets advanced and retreated through multiple glacial cycles over hundreds of thousands of years, they were essentially pre-building the architecture of the landscape that people would eventually inhabit. Depressions that would become marshes and lakes, ridges that would become dry ground people could walk on. The hills that eventually became the Dogger Bank weren't just a coincidence of geology. They were partly a product of this glacial reshaping, elevated enough to remain dry even as surrounding areas flooded first. But here's where the concept of a land bridge needs to be examined carefully because the phrase is technically accurate and simultaneously misleading. When most people hear land bridge, they picture something like a narrow strip of ground connecting two larger land masses, a corridor. Think of the Bering Land Bridge and you get the image. But Doggerland wasn't a corridor. At its greatest extent, it was a subcontinent. It wasn't connecting Britain to Europe so much as Britain was simply the westernmost edge of a continuous landmass that stretched unbroken to Scandinavia, to the Netherlands, to what is now Denmark. Calling it a bridge undersells it badly. The bridge terminology made more sense later in the story as sea levels rose and the land began to shrink and narrow, eventually reducing what had been a vast open territory into something that genuinely functioned as a corridor before disappearing entirely. But at its peak, Doggerland was the main event, not the connection between two other main events, now rivers. And this is where the reconstruction gets genuinely fascinating. We know that major rivers had to be crossing this landscape because we can trace where they went. The Rhine is the clearest example. Follow it on a modern map, and it terminates at the Dutch coast, emptying into the southern North Sea through a delta, but that's only where it ends now. During Doggerland's habitable period, the Rhine continued westward across the exposed plain, eventually being joined by what we now call the Thames, which also didn't terminate at the English coast, but continued as a tributary into this larger drainage system. Researchers have mapped what they call the Schnelled Rhine, a major river system that ran roughly through the center of Doggerland, collecting water from rivers draining both the British uplands and the continental European landmass, before finally reaching the Atlantic somewhere near what is now the English Channel approach. This wasn't a single straight channel. River systems never are. It would have braided and split and rejoined, with oxbow lakes forming and draining with seasonal flooding, creating temporary wetlands across the floodplain. And wherever a large river ran through a landscape, you'd have had exactly the kind of ecologically rich environment that Mesolithic people sought out. Water for drinking, fish in abundance. Waterfall concentrated around marshes and red beds. Game animals coming to drink at predictable locations. The river wasn't just a geographic feature. It was the organizing spine of the entire human geography of the region. But Doggerland wasn't just river valleys and open plain. And this is the point that gets missed when people imagine it as some uniform, featureless stretch of exposed seabed. The environment was extraordinarily varied. Soils across the region would have ranged from heavy clay deposits left by glacial meltwater to lighter sandy soils in areas where wind and water had sorted and redistributed sediments over centuries. In the lower lying areas, especially around the river systems, you'd have had peat-forming wetlands, the kind of boggy, waterlogged environment that is actually fantastic for preservation, which is part of why we find what we find. In drier, elevated areas, the soils would have supported grassland transitioning into open woodland as the climate warmed through the Mesolithic. There were coastal dune systems too, probably extensive ones, running along whatever the active coastline was at any given time. These dunes would have shifted and migrated as wind patterns changed and as sea level rise slowly pushed the coast inland. And between the dunes and the river systems, you'd have had estuaries. Those extraordinarily productive brackish environments where fresh water and salt water mix and where the density of available food resources tends to be higher than almost anywhere else on Earth. Hunter-gatherer populations across the world have always been drawn to estuaries, and there's no reason to think the people of Doggerland were any different. So, how do we actually know any of this? Because none of it is visible. It's all buried under 30 or 40 or 50 meters of seawater and a few meters of marine sediment on top of that. And the answer is that archaeologists and geologists have spent decades developing and refining techniques for seeing through water and through sediment to read the landscape that's hidden beneath. The most fundamental tool is bimemetry, which is essentially depth mapping the seabed. Modern sonar systems mounted on research vessels can map the texture of the seafloor in extraordinary detail. And those textures preserve ghostly traces of the old landscape. Ancient river channels show up as sinuous depressions. Old coastlines appear as subtle ridges. The elevated area of the Dogger Bank stands out clearly. It's not a perfect picture, but it's a starting point. Then comes seismic surveys. By sending sound waves through the water and into the seabed and analyzing how those waves reflect back from different layers of sediment, researchers can essentially see the stratigraphy of what lies beneath. Different sediment types, glacial till, peat, river sand, marine clay, all reflect sound differently. A seismic survey of the southern North Sea can reveal layer after layer of geological history. And buried within those layers are the old land surfaces that people once walked on. Sediment cores are the third major tool and in many ways the most intimate. You lower a long hollow tube into the seabed, drive it in, and pull it back up full of sediment that may not have been disturbed since it was deposited 10,000 years ago. A single core might contain pollen from ancient forests, insect remains, seeds, occasionally animal bones, or traces of human activity. And each layer of that core is a snapshot of what the environment was like when that sediment was laid down. Dating those layers with radiocarbon gives you a timeline. Comparing pollen profiles tells you what was growing when. Mapping multiple cores across an area lets you start building a three-dimensional picture of a landscape that no longer exists. The picture that emerges from all of this work isn't a featureless plain. It's a place with hills and valleys, with major rivers and their tributaries, with marshes and dunes and forests and open grassland and productive estuaries. A place that was genuinely different from one part to the next, and that would have offered genuinely different opportunities and challenges to the people living across it. That complexity matters because complex landscapes support complex societies, and the people who lived here were more complex than most people realize. So, if this wasn't just a blank empty field between two coastlines, what was it actually like to live there? Not in terms of geology now, but in terms of daily life, where you'd pitch a shelter, where you'd scare up dinner, where you'd take a risk, and where you'd avoid because everyone knew that was where the ground tried to swallow you. To answer that, you start with the simple question every hunter-gatherer group has to solve in every time and place. Where is the reliable food? On Doggerland, the answer wasn't one single habitat. It was a patchwork, a mosaic of zones that each did one thing especially well. People didn't live on the plain in the abstract. They lived on its edges. The edges of forests, of rivers, of marshes, of coastlines that were creeping inland year by year. Take the rivers first. Those big braided channels of the channeled Rhine system you just heard about were the obvious spine of the landscape. But they weren't the only game in town. You had tributaries coming off the British uplands, streams draining from low plateaus, backwaters and oxbow lakes in the floodplains. Around all of those you'd have ribbons of gallery woodland, strips of trees hugging the wetter soils rich in nuts, berries and browsing for animals. Move away from the river for a few hundred meters, and the ground begins to change. In some places it rises slightly and dries out, turning into open woodland or grassland where you could travel quickly and see game at a distance. In other places, especially in the shallow depressions left by ice or by old abandoned river channels, it goes the other way. It gets wetter. You step and your foot doesn't quite come back up as easily as it went down. That's where peat starts to form. That's where Doggerland begins to turn into a patchwork of bogs, fence and marshes. Those wetlands are inconvenient to walk through, but eologically they are gold mines. Shallow water means plants, which means insects, which means fish, frogs, waterfowl, small mammals and predators sitting at the top of that food web. It means reeds you can weave, tubers you can dig, nesting birds you can surprise, and migratory flocks that are absolutely not expecting a hunter with a bow standing quietly behind a screen of willow. The evidence we have from bones and pollen says Doggerland was exactly that kind of place, a wetland mosaic, not endless dry grassland, not endless swamp, but alternating patches, dry ridges, wet hollows, forested pockets, open areas, and everything in between. Now scale that mosaic up until it stretches from what is now Norfolk to Denmark. That's the world these people knew. In the drier parts, especially on slightly elevated ground and along sandy ridges, you'd have had woodland at different times dominated by birch and pine in the colder phases, then oak, hazel, elm, and other broadleaf species as the climate warmed after the last glacial maximum. The pollen records from cores pulled out of the seabed show these shifts quite clearly, and that matters because woodland isn't just scenery, it's infrastructure. Hazel stands, for instance, are a mesothic supermarket. The nuts are calorie-dense, store well, and ripen in predictable bursts. You can plan your year around them. You can move into an area in late summer or early autumn, camp on slightly raised ground near a river, and spend weeks harvesting, roasting, storing, and eating hazelnuts. Charred nutshells from sites around the North Sea basin suggest people were doing exactly this. Then there are the animals using those woods. We know from finds dragged up by trolls and from submerged deposits off the modern coastlines that Doggerland supported large herbivores or ox, the wild ancestor of domestic cattle, red deer, roe deer, and in earlier, colder periods, mammoth and woolly rhinoceros roaming the more open steppe-like parts of the plain. Over time, as the climate warmed and true tundra gave way to forest and mixed environments, the mammoth and rhino retreated or vanished locally. But the deer and aurochs stayed and thrived. Imagine seeing an aurochs in that landscape. This isn't a cow. This is a massive horned animal that can weigh a ton, built to plow through undergrowth and defend itself. Hunt one successfully and you feed a group for days. Fail to respect it and you have a very short career as a hunter. Red deer, on the other hand, are more agile, more numerous, and highly predictable in their movements. They like ecozones, those transition zones between forest and open ground. Dogland was full of those edges. That made it red deer country. And where there are large herbivores, there are predators, wolves, bears, lynx, probably other carnivores we haven't yet documented well in the submerged record. People moving across Doggerland weren't just looking for prey. They were also scanning for things that might be looking for them. But if big game hunting was the glamorous, dangerous side of life on the plain, the dependable calories came from water. Fish runs would have been the seasonal bonanza that shaped entire migration routes. Salmon and other migratory species use environmental cues, temperature, daylight, flow to head upriver at roughly the same times each year. Even with some youth-to-year variation, that predictability is incredibly valuable to a mobile hunter-gatherer group. You don't have to know the chemistry of dissolved oxygen to know that when the leaves are just starting to turn, or when the geese first appear overhead, the fish will be in the narrows of that particular river bend. You only have to notice that your grandparents always came here at this time, and always went away with more food than they could eat immediately. Set up camp on a dry knoll just back from the floodplain where the ground doesn't waterlog your bedding and you have a line of sight to the river. Build simple wee fish traps or lines. Smoke or dry the catch on racks for days or weeks. This one spot on the plain becomes the center of the world for your group. Then when the run tapers off, you move on. Waterfell add another seasonal layer. Wetlands in Dogland would have functioned like service stations on the Great Migration flyways. In spring and autumn, the skies above the rivers and marshes would have filled with birds resting and feeding as they moved north or south. Archaeological sites from other European wetlands showed dense concentrations of bird bones in Mesolithic layers. Ducks, geese, swans, waders, suggesting systematic exploitation. There is no reason to think Dogland was any different. Nets, snares, strategically placed blinds. All of this is simple technology, but when applied in the right place and season, it turns a marsh into an all-you-can-eat buffet. Plant foods in and around those same wetlands would have been equally important. Cattail and other red species have starchy rhizomes. Water lilies and other aquatic plants have edible parts. On slightly drier ground there are berries, edible greens, and in later periods, possibly wild cereals in more open patches. Processing those foods takes knowledge and labor, digging, peeling, roasting, grinding. But again, once that knowledge exists in a culture, the landscape turns into a pantry. Put all of this together and you start to see why this plain could support not just quick hunting foray, but repeated visits and in some zones extended stays that almost blur into semi-permanent occupation. Picture a year in the life of one hypothetical group. We're speculating here, but we're doing it within the bounds set by what we know from better preserved Mesolithic sites on the former coasts of Britain, the Netherlands, and Denmark. Winter might be spent in more sheltered inland areas, low ridges with forest cover, near springs or stable stretches of river that don't flood catastrophically. Here you rely on stored nuts, dried meat, and opportunistic hunting. As spring approaches, you move toward the wetlands and lower river valleys as waterfalls and early fish runs begin. For a few weeks or months, your group and perhaps an allied family or two cluster near an especially productive stretch of water. There's more food than you can use immediately. So, some of it is preserved, some of it is traded, some of it just goes back into the ecosystem. Summer sees smaller, more mobile groups fanning out across the drier parts of Dogland, targeting deer and aurochs, checking familiar groves for early fruits, repairing tools with raw materials collected in different parts of the plain. Late summer and autumn bring you back toward known hazel stands, berry patches, and maybe certain red beds where tubers are easiest to dig. You camp again and again in the same handful of places over generations because those places always deliver. You know where the ground stays dry in a flood. You know which noels catch the evening breeze and keep mosquitoes away. Over time, those repeated visits leave traces, hearths, scatters of flint flakes, discarded bones, the odd broken tool. Nothing like a village, but more than a random campsite. That's what archaeologists mean when they talk about persistent places in hunter-gatherer landscapes. Dogland, with its mixture of stable high ground, reliable rivers and recurring seasonal abundance, would have been full of them. But here's the catch. The places that were best to live in are not necessarily the places that are best at preserving evidence that you ever lived there. This is where the strange logic of the archaeological record comes in. The reason we know as much as we do about Dogland is not because it was such a good place for people, but because parts of it was such a good place for mud. Waterlogged environments, peat bogs, silty lake bottoms, low-energy backwaters are fantastic at locking away organic material. Exclude oxygen and decay slows dramatically. Wood, bone, plant remains, even footprints can survive for thousands of years if they're buried quickly under fine, wet sediment. The southern North Sea basin has large areas where exactly that happened as sea level rose and wetlands were gradually drowned and capped by marine clays. That's why we sometimes get preserved peat layers out on what is now the seabed, and why fishing nets occasionally bring up bone that's tens of thousands of years old rather than just yesterday's by catch. Those bones spent most of their post-mortem existence sealed in dark and toxic mud, immune to scavengers and weather. Sandy environments tell a very different story. Sand is great for drainage and comfortable campsites. It's terrible for preservation. Organic material in well-aired sandy soil breaks down quickly. Add the later action of waves, currents, and burrowing animals, and whatever fragile traces were left of a mesothelic campsite are likely to be scattered or erased long before anyone with a research vessel goes looking for them. Even within the wet parts of Dogland, preservation is patchy. Peat forms in particular conditions of waterlogging and plant growth. Change the hydrology slightly. A river shifts course, a dunfield moves, sea level nudges the coastline inland, and a peat-forming bog can first dry, then erode, then vanish. Some pockets survive, others are chewed up by later processes we can't reconstruct perfectly. Then there's the final insult: marine transgression. As the North Sea formed and deepened, waves and tides began to rework the upper layers of the old land surface. In some areas, sediments from rivers and bogs were preserved under a protective cap of marine clay. In others, the top few meters of the landscape were simply stripped away, like peeling back the surface of a painting and taking the details with it. So when we talk about life on the plain, we're doing it through a filter. We see the bits that survived in peat, silt, and sheltered basins. We see bones that were lucky enough to be buried in low-energy settings. We see the durable things, flint, stone, the densest parts of skeletons that can handle being jostled around on the seabed for a few thousand years. What we don't see most of the time are the ephemeral structures, the wooden stakes of fishes, the frames of shelters, the woven mats, the bags made of leather or plant fiber, the children's toys, the carved sticks that might have carried stories. Those existed. People don't stop making culture just because the soil is bad at remembering it, but the sea is often indifferent to our desire to know. And yet, even through that bias, a coherent picture still emerges, a landscape that was not marginal, not a desolate bridge people sprinted across on their way to somewhere better, but a rich, varied homeland in its own right, a place where generations grew up knowing particular bends in the river, particular corpses of trees, particular marshes where the geese always seemed to land. The tragedy and the opportunity from our perspective is that so much of that world is now gone twice over. First drowned, then partially eroded. What's left is scattered, fragmented, often recovered accidentally by people whose job isn't archaeology at all. Which brings us back to the fishermen and to the bones in their nets. Because if life on this plain was as rich and as long-lasting as the environmental evidence suggests, then there weren't just animals out there. There were people. And some of them died on that land, were buried in that soil, and are only now beginning to surface again. So, who were they? Not in the vague sense of prehistoric people, but in the more precise sense of what kinds of humans walked across this land, camped beside these rivers, watched those hazel groves ripen, and those marshes fill with birds. The answer spans a long stretch of time. Dogland wasn't a single-moment world. It was a stage that saw different castes walk on and off. From late Ice Age hunters following herds across an almost Arctic plain to Mesolithic foragers weaving their yearly routes through a warmer forested landscape. If you roll the clock back to the late Paleolithic, before forest had really taken hold, the people moving through this region were part of what archaeologists often call Magdalenian and Hamburgen and Federer cultures. labels that mostly refer to their stone tool styles and the sites we found on what is now dry land around the North Sea basin. They almost certainly cross bits of what would later become Doggerland. But for them this was a cold, open steppe with reindeer and maybe the last local mammoths and woolly rhinos as the main game. Think of them as highly mobile specialist hunters keying in on big herds and covering huge distances. By the time Doggerland becomes the lush wetland mosaic we've been talking about, we're mostly dealing with what archaeologists call Mesolithic groups, post-glacial hunter-fisher foragers who lived roughly between 10,000 and 6,000 BCE in this region. These are the people whose lives map most closely onto the hazel groves and salmon runs and bird migrations we just walked through. And while they had regional tool styles and subtle differences from place to place, genetically and behaviorally, they were the same kind of humans as us. Homo sapiens from the same bottlenecked stock that had spread across Europe thousands of years earlier. One thing we can say with some confidence is that they weren't living in big permanent villages spread evenly across the plain. The evidence from well-preserved Mesolithic sites around the North Sea rim, Starkar in Yorkshire, Tybrandt Vig in Denmark, Per sites in the Netherlands, all point to small groups, probably on the order of a few families banded together, maybe 20 or 30 people most of the time, sometimes more when groups converged for seasonal gatherings. Dogland for them wasn't a single home village, but a network of places that were stitched together by movement and memory. Archaeologists sometimes talk about mobility strategies and resource scheduling, which sound like PowerPoints, but really just mean this. You don't wander around at random. You move in patterns that match when and where things are worth the effort to get. Those hypothetical spring fish camps, they weren't improvisations. Groups would have known year after year that this bend or that ford pays off when the water reaches a certain level or when the first particular flowers bloom. Hazelnut groves, berry thickets, good deer stalking grounds. All of these come online and shut down again on fairly predictable schedules. So, a Mesolithic year in Doggerland probably looked more like a well-rehearsed circuit than a random walk. You might think of one group's range as a kind of invisible loop over the map. Wintering on more sheltered wooded ridges in what's now eastern England, spring fishing in channels that now under the central North Sea. Summer hunts along sandy uplands closer to what is today the Dutch or Danish coast, autumn nut and tuber harvest somewhere in between. Another group hundreds of kilometers away had their own loop that overlapped at a few strategic points, a productive river mouth, a good crossing point, a patch of flint-rich gravel where people from different bands might reliably bump into each other every few years. Those overlapping loops repeated over generations create social and mental maps. Places get stories attached to them. This is where your grandmother killed the biggest deer. This is where we first met the people from over the water. You don't build stone monuments, you build narrative ones. What about the camps themselves? If you walked into one at the height of the season, it would not look like a town. It would probably be a fairly low-impact sprawl of shelters and hearths clustered on slightly higher, drier ground with access to fresh water and a line of sight over whatever resource had brought people there. The ground would be littered with the debris of daily life, most of it invisible to us now. Plant fibers, discarded bits of wood, scraps of hide, footprints trampled into the mud. Mixed in would be the things that survive. Flakes of flint where someone sat and sharpened a tool. Fragments of bone and antler from butchery and craftwork. Maybe a few burned nutshells and fish bones around hearths. And in people's hands and belts and bags there was technology. When you hear Stone Age, it's easy to imagine crude, chunky tools. But by the late Paleolithic and Mesolithic in this region, the toolkits had become incredibly refined. One of the hallmarks of these societies is the microlith. Tiny, carefully shaped stone blades and points, often less than a few centimeters long. On their own, they look like slivers of broken glass. In context, they're components. The trick is in how you use them. Instead of making one big stone spear point, you make many little blades and embed them in wood or antler to create composite tools. A row of microliths set into a grooved shaft becomes a barbed arrow. A single sharp sliver hafted at the right angle becomes a cutting edge for a small knife or scraper. If one edge breaks, you replace that module without remaking the whole tool. That modularity is a logical answer to a mobile life. Flint isn't everywhere, and good flint is even rarer. On Doggerland, people would have known the locations of flint-bearing gravels and chalk outcrops and planned their movements to hit those spots, stockpiling raw material when they could. Once you've gone to the trouble of acquiring good stone, turning it into a kit of interchangeable multi-use microliths is just efficient. Stone was only part of the story. We know from waterlogged sites on the modern coasts that bone, antler, and wood were central to Metallithic technology. Antler, especially from red deer, is strong yet workable. It turns up as pick-like tools, barbed points for hunting fish and waterfowl, and as handles for stone inserts. Bone harpoons and fish gigs with multiple prongs show up in submerged finds around the North Sea. These aren't generic poking sticks. They're carefully shaped implements designed for specific prey and environments. And then there's woodworking, the vanished majority of their technology. Wherever we get glimpses of mesolithic wooden artifacts in those rare anoxic lenses where wood has survived, the picture is immediately more complex. Dugout canoes, paddles, stakes from fish, worked planks, sometimes even fragments that look like parts of frames or platforms. There's no reason to think Doggerland was an exception. On a low-lying river-laced plain, wood would have been turned into everything from spear shafts and bows to drying racks, trusses for shelters, and the ribs of boats. Boats matter in this story. At some point, probably quite early, Dogland wasn't just a place you walked across. It was a place you crossed by water. Channels deepened, rivers widened, and sea level rose in pulses. A group that had always forded a river might a few generations later need a canoe or a raft. Islands formed on what had been continuous land. Knowing how to cut, hollow, and balance logs, how to read currents and wind, how to time tidal flows, that's not optional knowledge in a landscape that is slowly disintegrating into archipelagos. We can't listen to their conversations, but we can see hints of their social world in the way materials move. Some of the flint found on submerged or coastal megalithic sites doesn't match local geology. It comes from distinct sources hundreds of kilometers away. That means either people with flint traveled long distances or the flint itself passed hand to hand along chains of exchange. Probably both. And it wasn't just stone. Exotic shells, amber, distinctive rock types. These tiny anomalies in the archaeological record suggest that Doggerland's inhabitants were plugged into broader networks stretching from what is now the Baltic through northern Europe and into the Atlantic facade. Not every group knew every other group, but ideas and materials could move farther than individuals usually did. This has social implications. If you're exchanging material over long distances, you probably also exchange stories, songs, spouses, and obligations. Marriage patterns in small mobile societies tend to reach outward both to avoid inbreeding and to build alliances. Genetic studies of Mesolithic remains on dry land hint at these structured relationships. Individuals buried in one place sometimes carry ancestry linked to distant regions. Dogland's rivers and coasts would have been the highways of this world. And crucially, people who live by tides and currents for generations don't treat them as mysterious. They learn the pattern. Imagine growing up where a large part of your food comes from fish runs and shellfish beds. You'd know the phases of the moon not as an abstract astronomical cycle, but as the rhythm that decides when certain sandbanks are exposed, when river mouths are easiest to net, when dangerous currents slacken. Knowledge of tides and river behavior in Dogland was not esoteric lore. It was the difference between an easy crossing and being swept into deeper water. There were probably shared places tied to those rhythms, spots where neighboring groups expected to meet in certain seasons, a particular estuary when the fish were running, a certain hazel-rich ridge in autumn. At those nodes, life would have looked different from a small family camp. More shelters, more hearths, more children running around, and most likely more ritual, whatever form that took. We have to be careful here. It's tempting to project detailed social structures and spiritual systems into a landscape we find evocative. Did Dogan's people mark coming of age with ceremonies on particular hilltops? Did they tell origin stories about the rivers or about animals that had vanished from living memory like mammoth and rhino? Very possibly. Hunter-gatherer societies around the world invest their landscapes with meaning and narrative. But beyond a few enigmatic finds, red ochre traces, unusual placements of bones, the occasional carved ornament, most of that inner life is opaque to us. This is where the line between responsible inference and speculation matters. We can say with a fair degree of confidence that small mobile groups of modern humans used Dogland intensively during the late Paleolithic and Mesolithic. They moved in patented ways, tracking seasonal resources and revisiting persistent places across years and generations. Their toolkits were sophisticated based on microlithic stone technology, bone and antler craft, and extensive but mostly lost woodworking. They had the practical knowledge to read tides, rivers, and animal movements. And they participated in wider networks that move materials and probably people over long distances. We can suspect based on analogy with other foraging societies and on the few symbolic objects we do find that they had rich oral traditions tied to particular landmarks. They marked some deaths or events differently from everyday disposal of bodies and trash. They used shared gathering spots as venues for exchanging not just food and tools, but stories, songs, partners, and obligations. Beyond that, we step into real uncertainty. Did they have named clans or totems? How did they resolve conflict between groups? What did they think was happening when generation after generation the sea quietly ate bits of their world? The material we have doesn't let us answer those questions cleanly. What it does let us say is that these were not anonymous wanderers on a blank map. They belonged to this place. They knew it intimately. They saw it change. And that brings us back to the bones in the nets. Because to move from a general picture of people like this lived here to this particular fragment of skull, this jaw, this child's fever came from a person who once stood on that ground requires a different kind of evidence. Not just environmental reconstruction, not just analogy, but hard clues from the seabed itself. Those clues exist. They're rare. They're fragile, and most of them arrive on deck coated in mud and mixed with fish. But together, they're starting to anchor this lost world to real individuals. So, how do we get from a troller's winch to a story about who those individuals were? That's where the science gets clever. For archaeologists, the North Sea is a paradox. It's overflowing with evidence, and almost none of it is where it's supposed to be. Start with the most unglamorous but surprisingly rich source of data: fishing by catch. If you talk to trawler-men who've worked the North Sea for decades, they'll tell you that pulling up old stuff with the nets is just part of the job. You're aiming for cod or plaice and up comes a reindeer antler. You're hauling sand deals and discover a chunk of peat, black and fibrous, that crumbles in your hand and smells faintly of a long dedad marsh. Mixed in with the fish, there are sometimes worked flints, sharp little blades and points that definitely didn't grow there, and every so often bones that are very obviously not from cod. To the fishing industry, this is debris. It rips nets, clogs gear, wastes time. To archaeologists, it's accidental archaeology. Samples from a drowned landscape that no one set out to excavate. The first thing to understand is that the seabed of the southern North Sea is not a smooth, static carpet. Trolls scrape, storms scour, sandbanks migrate. Old river channels are filled, then recut. Peat layers are exposed, then buried. So when a trawler drags a heavy beam or otter boards across the bottom, it's not just disturbing today's sediment. It's shaving off thin slices of geological time. If the net happens to bite into the top of an ancient channel filled with silt and bone, you might suddenly get a haul full of mammoth teeth, bison vertebrae, deer antlers, and once in a long while, a human fragment. If it crosses a patch where an old peat bog has survived under a thin sand cover, you get huge black clouds in the codent. Sometimes with plant remains so well preserved, you can still recognize leaves and seeds. Every haul is an uncontrolled core sample through layers that were once dry land.